And the last few things about me, really quick. Yeah, I live here, like I said, in Oklahoma City with my wife and my 3 girls. I enjoy everything hockey, ice hockey, RC flying, biking. I love being outside, camping and traveling. So I definitely, this is not my environment sitting at a desk. It is at work. That's where I'm at. But right when those 8 hours are up, I am outside. I love being out and being traveling and exploring and being with my family. So originally from Salt Lake City, Utah. And again, like I said, moved here to Oklahoma City, and we love it out here. So yeah, I'm looking forward to getting to know you guys. I also want to say that I've been able to develop a relationship with a number of different students over the years. A couple of them have reached out to me saying they got jobs just this last few weeks in different airlines, and we still stay in touch. So we'll have that opportunity to do the same. And I always look forward to hearing everybody's success stories down the road. I'd love to get to know each and every single one of you tonight. I know that's probably not going to happen. So usually what I do, and Betty as our returning student saw this last time, but I have 3 different categories and 3 different scenarios that I'd like to put you all in. And if you fall under one of these categories, I'd like you to raise your hand, okay? And I'm just going to pick from a few of you that do raise your hand. The first category is I want to see the group of individuals, and you can raise your hand electronically, the group of individuals who have no aviation experience at all. And we'll go from there. Let's see here. This is all a little laid out differently than last time. Sorry, guys. All right, I got to go with, is that Nichelle? Okay, my wife's middle name is Nichelle.
And I.
Yep, I love that name though. Yeah, we named one of my daughters. That's her middle name as well, is Nichelle. So, but yeah, tell me about you. You're coming in here with 0 aviation experience. What led you here?
Well, the only aviation experience I have is I travel. I took because my boyfriend, he actually works for Delta. He's on the line, so he's a mechanic. So okay. A lot of the terms I do hear from him, and I always ask him, well, what does that mean, or what is this, what is that? But this class has been a little bit more of a challenge for me because to me it feels like this is a foreign language. But I'm still here. I'm trying. That's all I can do. I reach out to whatever resources I have to try to help me understand. Good. So what led me here is many years ago, I used to do police dispatch, left that. Then I went into retail, just recently left retail. And I was trying to get back into police dispatch, but that wasn't going as planned. And I just happened to be scrolling on Facebook and I saw an ad for this school and I checked it out, did some research, had some people dig into it to see if they could see if the school is legit, and it turned out to be legit, and here I am.
Well, that's exciting. Well, I'll say that your jump seating experience, behind the pilots in the cockpit are going to be much more enjoyable than any police ride that you get from them. So you made a good choice. I think you'll enjoy the traveling, those different perks that come with it. So yeah, Nichelle, that's great. Thanks for sharing. Let's go with Brian. Do you mind sharing? And then we'll have Trevor too. I mean, this group is really important to me because you guys are coming in here with no experience. So we'll start with Brian first.
Yeah. So this is a midlife career change for me. I was a software developer for about 25 years. Got laid off a couple of years ago and been spending the last couple of years just kind of figuring out what to do with my life. So actually didn't know about dispatching specifically. I mean, at least not something that you could, in your midlife go out and go for. Yeah. I met a guy at a party and he was like learning to be a pilot. And he said, you should do dispatch. And so I was like, I looked into it. Well, I actually, 2 of my, lifelong hobbies, I've always been a huge meteorology fan. And I've always enjoyed navigation, not necessarily specifically aviation, but just, I guess maritime and aviation. I just like the whole process of it.
Awesome.
And so, and I like to track flights and do nerdy things like that. So
Oh yeah.
it just seemed like a great fit. So I was really excited to get into it.
Well, that's great. So yeah, just something last minute decision. You're like, I'm doing it. I'm going for it.
Yeah, pretty much.
That's good. Hey, well, good luck to you. And we're here to help. You know what I mean? You're not doing this by yourself. So
Yeah.
You pay for this course and you get lifelong friendships. It's pretty cool.
That's great. Yeah.
Yeah. Well, Trevor, let's hear from you.
Yeah. Obviously new for me, all new stuff for me too. But I've been in restaurant management for quite a few years, and but I've always been interested in aviation and kind of have looked at different jobs over the years and thought about making a transition. But I'm another person who didn't know about dispatch until relatively recently, and just something that seems interesting to me. And so here I am.
That's excellent. That's great. That's awesome. Well, that's always a fun category for me to listen to, because it's like, what in the world got you here? Like, that is crazy. So yeah, I love it. You guys. Let's go to the next group. Can I see the hands of those that have 5 years or less of aviation experience? Even if it's like a week, right? let me see what we got here. Let's go with who do we have? Caitlin. We'll go with Caitlin first. And I'll just do a couple from this group. Sorry, guys. I won't get to everything.
So yeah, I got into aviation when I was 17. So in high school, I did a discovery flight and loved it. So I thought I wanted to be a pilot. So I pursued that through high school. At the end of high school, I got my private pilot's license. And then I originally went to Purdue University for their flight program. And then after my first year, I was like, yeah, I'm feeling pretty burnt out. So I switched over to aviation management just because I still loved aviation. And I figured that would give me a lot of options career-wise, because I still really wasn't sure like exactly what I wanted to do. So since I graduated, I worked at a flight school in New Smyrna Beach, Florida, with one of the instructors, actually, Jen. She was my manager.
Oh, was she? Okay, yeah, I did. Yeah.
But I worked there for like a year, and then I moved over to Spirit Airlines and work in their operation department. But I kind of I'm like a little bit of a nerd. Like, I like to do analytical stuff, look at the weather, do math, all that. So I've always wanted to, I don't know, like maybe for the past 3 years, I've been thinking about dispatching. So now that I'm 23, I was like, this is a pretty good time to do it. So.
Absolutely.
Yeah.
Absolutely. So that's good. You've been around it. You've been at an airline. This is great. That's a good fit for you. That's awesome. Let's see here. Who else do we have? Muhammad, you want to share with us kind of your 5 years or less of aviation experience?
So hello. And I got into aviation because I'm project manager, right? And I was kind of pursuing that, but I wanted the flight benefits. So I joined the REN part-time, right? And I got into dispatching a little bit. I was dispatched for de-icing. And then I figured instead of just trying to manage 2 jobs, why don't I just try to go for something still in aviation, right? Keep the flight benefits and still make it a career, right?
That's
so
awesome.
I got told about dispatching, and I looked into it, and I was like, hey, it's pretty sweet. So got into it.
That's good. And so, I'm sorry, did you say what airline? I didn't hear that.
United.
What was it?
United.
Oh, United. Okay.
Yeah.
Cool. So where are you right now? Do you live at one of the big hubs? Are you in?
Yeah, I'm like 5 minutes away from Dallas.
Oh, okay, good.
Yeah.
Awesome. That's great. Okay, cool. Let's see. Let's do one more. Who do we have? Is it Tatum? Or
Yeah, it's Tatum.
Tatum, right?
Yes.
Okay. Cool.
Mm-hmm. My grandpa flew for Delta, my dad flies for Delta, and my dad, I live like just south of Atlanta in Peachtree City, and my dad has a hangar and like a little small 4-seater plane. And so I took flight lessons for a little bit, decided it wasn't for me. And then I hopped around, worked at Old Navy, Disney World. Now I work at Chick-fil-A, and decided I should probably do something with my life and my dad's always told me about dispatching. So I was like, oh, I'll give it a try.
Yeah, it's a guy
And-
who knows something, a thing or two about dispatch. That's
Mhm.
good. Yeah, that is awesome. Well, thanks for sharing. All right. Is there anybody out there that has more than 5 years of aviation experience? More than 5 years. We got Christopher. Do you go by Christopher or Chris? Does it matter?
Go by Chris.
Chris. All right. What's up, Chris? Yeah.
Yeah, I guess I have a couple of years of aviation experience. I'm a civil engineer turned marine pilot. I flew C-130s, King Air 350s, and I was in the unmanned world for a couple of years as well.
Awesome.
Retired in 21, kept instructing out in Kuwait, Bahrain as a C-130 instructor. And I went med down. They offered me a part-time dispatching gig, remote, which has been absolutely sick. And they just recently offered to give me full-time back out to Kuwait. I'll be heading out in May.
Oh, really?
So yeah, that's part of the reason I'm taking the course. They had started mentioning this early January. And I said, well, hey, I should go get certified. And they said, yeah, you should. So here I am, getting certified. So I'm a nerd to the third power, I guess, after I get my dispatching certification.
That is so cool. So do you know okay, so you have military experience. Did you ever hear about TERPs?
Yes.
Okay.
That's your world, yeah.
Yep, that is definitely my world. Yeah, but I work with a lot of guys who are, they're retired from the Air Force, flying C-130s and stuff, and they come and become TERPsters. So
yeah, Air Force, they're huge into that. So they do a lot more airfield design. And the Marine Corps will go they'll go set up a 3,000-foot long by 60-foot wide strip and say, here you go, land on it.
right.
Which is fun, but not really that much fun. So yeah, I mean, I've flown a lot of approaches in a lot of countries all over the world, and it's always baffled me the amount of work that has to go into building those approaches. And I've seen some doozies, especially flying in SoCal, and flying in places like Indonesia, where you're flying, you're basically flying off 80. Sorry, my cat just went ballistic. You're flying off radio signals. They don't even know what an ILS is. Yet the approaches are still built to a standard where you can say.
Yeah, you definitely have you have an appreciation for that. That's pretty cool. That's awesome. Well, thanks for sharing. And that sounds interesting. It really does. Betty, have you had an opportunity to share with this group kind of your background? Do you mind sharing again for me what your background is?
Yes, I did on the first day on the 12th, Monday. And as I mentioned, I have airline experience over 25 years, but not as a pilot, but as a flight attendant, 10 years with several airlines, basically mostly Asian. And also in the Middle East for Saudi Airlines. I lived there, yes, for many years. And I returned to United States and worked in the office for Northwest Airlines, which is currently Big Five merge, become Delta. And then I end up with United as a global services representative. They obsolete. They obsolete.
I didn't know you were with United now. That's great.
No, I'm not. I left. I don't like it.
No, I don't like it.
No.
Okay.
Yeah,
okay.
Muhammad did not his hate. Yeah, it was a lot of. I don't know. It's very different. So I can't stay that kind of environment.
Okay. All right. Yeah, I get it. Well, thanks for sharing. And I guess, Pete, you're the last one on in that list. So let's go ahead and hear from you, Pete.
Okie doke. I sort of, I just retired 26 years with the Highway Patrol here in California and live in just north San Francisco in Napa. Currently grew up in Southern Cal, but up here now. And flew as a helicopter pilot for 18 years with CHP, just retired a year ago.
Okay.
Spent 6 months up in Alaska flying tours and, you know, did a few things before CHP, but, you know, now I'm wondering what's coming next. So this is 2.5 or 3 or 4.0 possibility.
That's great. That's awesome. Yeah, I love it.
Happy to be here. Yeah.
Oh, yeah, happy to have you guys. You know, it seems like we have a lot of, you know, Caitlin, Chris, Pete, and everybody who has, you know, either your private pilot's license or any flying experience at all. Could you please raise your hand for me? Just so I can kind of gauge the amount of individuals with aviation experience. Okay, this is probably the most I've ever had in one class. Now lower those hands and then really quick for me, because this is a big deal. This is all about dispatch, right? How many of you have flown IFR? And those of you who know what that is, you'll know. Okay, I just need to, okay. Perfect. All right. Again, more than I've ever had in one class. So excellent. Thank you. All right. Well, let's get started. I'm just got a couple other things for you. Just housekeeping items. Please make sure that your, you know, per the FAA, we have to make sure that your webcams and your cameras are turned on. They want to see your engagement in the class for you to receive your credit. It also helps me as an instructor to kind of gauge who's paying attention, who's completely lost, right? It just makes the interaction a little more positive. It's a lot better environment when we can see each other, interact with each other. So make sure, just again, as a reminder, to please keep that on. At the end of today in our course, I will be sending out through the Google Classroom forum. I'll add the slides that we're going to go through today. Okay, there's a lot of words on here, and they're there for you to refer back to later on. I'll try not to read all the slides because that's really boring. That's not how I typically teach. But those words and everything are there for you to refer back to later on so that you can relearn everything in a slower pace. All right, so you can take your notes and come back to class maybe with some questions. I will also add, in addition to those slides, I want to add 2 YouTube links for tomorrow's class. I'm going to assign that to you as homework. They're not very long videos for my IFR flyers out there. It's just going to be a quick little recap. But those are 2 important YouTube videos that I do want you guys to watch in preparation for tomorrow's class. Okay, so please make sure to look out for that. Trying to think if there's anything else. And again, we're just going to take our standard breaks. So in about 30 minutes from now, we'll take our first break and make sure you guys can get up and walk around and not get too bogged down with the material that we're going to cover today. Betty, did you have a question? I see your hand raised before we get started.
Sorry, I forget to remove it.
Oh.
I'm so sorry.
Nope, you're fine. You're fine. All right, guys. Well, the past few weeks, you guys have gone through a lot of material, right? This is an 8-week course. Week 1, you guys learned about the FARs, the Federal Aviation Regulations, the rules. How much fuel do I need? And what's required on a dispatch release, right? All that fun stuff. Week 2, you guys remember what you learned about week 2? Any idea? I know, I'm really fishing here.
Aircraft performance.
Yes, aircraft performance. So you guys learned about max takeoff weights, landing weights. How much fuel does the CRJ 700 carry? How much does it burn? You know, the fuel, how much fuel is burned per hour? What is a pneumatic system, right? The engine bleed, the flaps, all the different flight controls. So those are all important things that you as a dispatcher need to know, because as you're dispatching, things will break. And you guys also learned about MELs, minimum equipment list items, CDLs, right? Configuration deviation lists, things that are either missing or broken. There are limitations to how your flight can be conducted when things are either broken or missing. So as you continue on this journey in dispatch, right, the aircraft systems and understanding aircraft systems is going to be a huge benefit to you. Week 3, you guys did aviation weather. So things that I think Brian, right? You said you're an aviation, like a weather geek in a way, right? I'm sure you love that. There's a lot of material there. I am not the weather professional, so it's a lot of material for me, but it is an important aspect of our job as dispatchers. Okay, to make sure that we're routing our flight in good weather, so that we get those smooth rides. We're outside of icing conditions. We don't want to put our flights into hazardous situations. So those are things that we need to be aware of and be able to read those pilot reports that are out there to help us with our decision making. And then it leads us to here right now, week 4. Again, week 4, week 5, this is where we start talking about navigation. This is the intro to navigation. So this is where you're going to begin learning the terminology with things that are talked about with regards to flight planning and just understanding what components are out there in the NAS, in the National Airspace System, that help our pilots navigate from point A to point B. And as you can imagine, there is a lot of material to cover. And luckily for a handful of you all who have been in aviation for a while, those of you who have been flying, this section is going to be a lot easier for you to understand than somebody, let's say like Nichelle, right? And Trevor, who are coming into this with no aviation experience at all. And I am going to try my hardest, Trevor, Nichelle, and those others who are coming into this without any aviation experience, to keep things at a level that can be understood by somebody outside of the aviation industry, okay? But it's just going to naturally happen where something is going to go over your head. If you need me to provide further clarification, let me know. Stop me. Let's talk about it. This is the time to do it. And then also after class and, during the day tomorrow, if you have a question, send me an email. We can make sure that we clarify what we're talking about. But at no point do I want anybody getting frustrated. Okay? We know that these concepts are sometimes hard to understand, and they're going to revisit a lot of these things during your in-person portion of your training in St. George. Okay, you're going to be able to hear some of these things again and then apply them. And with that application, that's where you're able to learn the best. So I unfortunately am tasked with introducing everybody to this, right? So this is where it's not the easiest set of things to talk about because they are complex and it can be challenging to understand, but we're here for you and we want to make sure that you guys are understanding these concepts to the best of your ability. So with that, let me go ahead and share my screen, move things around, and give me a thumbs up if you can when you can see my intro to navigation slide. Everybody see that? All right. Okay, so here we go. We're going to get started. Like I said, we'll discuss the air navigation basics. And let me move this around. Sorry, guys. This is, like I said, a little different than, it's like they updated Google Meet since November. There we go. All right. So we'll talk about air navigation basics, the different types of navigation that are used. We'll talk towards the end of our day today, we'll dive into instrument departures and arrivals. And if we have time, I'm not too worried about this section here. This is introducing the different navigation systems that are used inside of the cockpit. Okay. All right, so air navigation basics. Air navigation is going to be that process of piloting an aircraft from one geographic position to another And it introduces the need for planning, which your planning is going to include, even during the in-person portion of your training, you're going to be required to plot a course from point A to point B. They're going to teach you how to do that. You're going to need to measure distances. You're going to have to obtain different pertinent weather information. You're going to have to compute the flight time, determine the different headings, and ultimately the fuel requirements. So back in the day when I got my dispatch certificate, right? And for you pilots out there, you know what these things are: the plotter, the E6B, and a calculator, right? A flight calculator. These are the things that we were using years ago. I am happy to announce that we are using SkyVector in class. If you don't know what SkyVector is, no worries. Next week, I think on Friday, Thursday or Friday, you guys are going to have another instructor with you that's going to introduce what SkyVector is. And SkyVector is just simply an online platform that allows you to plan a flight from point A to point B and put in different points along your route. It's really cool. And it plots it all out for you, and it's all digital, and it makes the process a lot easier than the process of having to use paper charts or maps and plot your course. So lucky you. And then with air navigation, the basics, you've got to know and have an understanding, right, of what latitude and longitude is. Those are also referred to as parallels and meridians. So to keep things simple, we've got the equator here, this yellow line, and I'll try to zoom in. The equator here is going to divide the northern and southern hemisphere. And you have these other lines of latitude in yellow going all the way up to the North Pole and also to the South Pole, okay? So you have lines of latitude, that's the yellow. And then you also have the lines of longitude. So those are those long lines from north to south. And that helps measure and divide up our western and eastern hemisphere. Okay. And go to this slide here to show that. Things that we probably already know, right? But you've got to be able to understand that. There's longitude west and longitude east of what we call the prime meridian. So for example, Washington, D.C.'s basic lat and long, or latitude and longitude, it says Washington, D.C. is 39 degrees of latitude. So somebody tell me, 39 degrees north of what? What is that referring to? What are we north of? The equator. Yeah. Thank you. And you guys can respond. You can unmute if you'd like, but if you have to, you can go ahead and chat and send me your answers that way as well. I can see that. All right, so we're 39 degrees north of the equator, and it says that it's 77 degrees west longitude. Again, west of what? We're west of the prime meridian. So we have to go west 77 degrees. So about right there. And then we have to go north 39 degrees. Boom. And there's Washington, D.C. Woo. Okay. Same thing can be done with Chicago. We'll say that we're, 42 degrees north latitude. And what did it say? 88 degrees west. So here's 90. So it's just going to be a little bit to the east of this line, right? And there's your Chicago. Any questions with that, you guys, with the latitude and longitudinal lines? Pretty basic? Okay. Here's just another depiction of the prime meridian, which passes through Greenwich, England. Anybody been there? Raise of hands. Kind of fun. You can stand on both the Western and the Eastern hemisphere. And you'll see this depicted on a globe with this white and black dashed line running through Greenwich, England, and portions of Spain. I say Spain because I live there. It's my second home. I love Spain. All right. Any questions with that? Feeling pretty good there? Okay. Here are some other topics we need to understand. We need to understand the difference between a true course versus a true heading. So this solid red line here is depicting a true course of 070 degrees, okay? True course. And right here, this dashed line is showing that this aircraft is kind of cockeyed a little bit over here to the left. And it has a true heading of 65 degrees. So you can kind of see here, there's wind coming over here from the left-hand side of the aircraft. And what they're doing is they're turning the aircraft a little bit into the wind. So the heading of the aircraft has changed so that they can maintain a specific track along the ground. Okay, that's their true course. And we're going to talk about this a little bit more, but I want you guys to be able to understand that the aircraft's nose is not always pointed in the direction that they want to go, right? And that's because of wind. So if wind's pushing me over here to the right, I got to move my nose over here to the left a little bit so that I can maintain that straight track along the ground in front of me. And you'll see that a lot. And as a dispatcher, when you plan your flight, you draw this solid red line from point A to point B. And in class, when you do that, you're also going to have to take into account the wind, and your true course may not match your true heading because of the wind. And this is just an example of that. So please make sure that you guys understand that concept, that my heading may be different than my course because of wind. Okay. And you guys are going to get all these slides, don't forget, right? And it's going to be mentioned again. We're going to talk about this a lot. All the fun stuff. All right. Any questions with that, you guys, before we move on? Okay. All right. So the magnetic compass in the aircraft, okay, is always pointing to the constantly shifting magnetic North Pole. Okay. So we know that we have a true North Pole that never moves. Okay, it never moves. It's just right there at the top of our wonderful Earth, right? And this true north is what all of our maps and all of our aeronautical charts are based off of. Ignore all the red lines right now in this image. Can everybody see the gray lines that are depicted on this map? Okay. That is what your maps are based off of. All of the maps, all of the paper charts that we look at are all based on the longitude and latitude lines that you see here in gray. Okay, they're overlaid on top of the globe here. But we also know that there is a magnetic field out there that our magnetic compass is going to point to. The magnetic compass in the aircraft, or the magnetic compass you had wrapped around your neck as a child, right? Running around in the backyard. That magnetic compass is pointing to this magnetic North Pole. So it's not pointing at true north, but rather the magnetic North Pole. Okay, so keep that in mind, that the thing that I'm using, right? My equipment is pointing at this magnetic North Pole, yet my maps and everything are oriented to this true North Pole. That means that there's going to be some, you're going to have to compensate for that difference at some point. And I'm going to show you what and how we do that. Okay. So just know that the aircraft's magnetic compass is pointing to, it's wanting to point to this magnetic north. So there are certain areas in the United States, well, anywhere really, but we're just going to focus on the United States, where the differences between true north and magnetic north are very different. Okay. And this difference is referred to as variation. We call it magnetic variation. What is the difference between the degrees to true north and magnetic north? Okay, there's a difference there. Now there's a location, and it moves from year to year, but there's always a location where your magnetic north and your true north are equal. They're the same. And that location where there is no variation is referred to as the agonic line. Okay, see where it says, it's kind of hard to see. Let me zoom in a bit. It says 0. Okay, that's the agonic line where there is no difference between true north and magnetic north. The magnetic compass, if your aircraft is in this location and you have the aircraft pointing to true north, your magnetic compass is also going to be pointing to the north. There's no difference. Now, the lines showing variation amounts between true north and magnetic north are called isogonic lines. And you guys really aren't going to be tested on the agonic line, isogonic lines, right? I'm just trying to provide you with information of, reality here, that there are these different names out here, and you at some point you will need to know this, but I wouldn't get too stressed about it at the moment. Okay, so there's a place where there's no difference, and then everywhere else where there is a difference, we call these isogonic lines. So an aircraft flying west of the agonic line, so over here, can expect its compass needle to point to the east, while an aircraft flying over here east of the agonic line can expect its compass to swing more to the west, because remember, that magnetic compass is always going to want to point back to where that magnetic North Pole is located. Okay, and here's a different depiction of that explanation. So we'll start with the middle one here. Okay, and look at my aircraft. I've got an aircraft where its nose is pointed to the North Pole, the true North Pole. And I'm at that part of the country where the agonic line exists, right? And remember, the agonic line is where the magnetic north and the true North Poles are the same. There's no difference. There's no variance in the two. So therefore, my aircraft is pointed to true north. Look at my magnetic compass. It wants to point to the magnetic North Pole. And in this location, it's the same as the true North Pole. So my magnetic compass is reading correctly. Now let's look at a different example here, where again, my aircraft is truly pointed to the true North Pole. But look at what just naturally happens to my magnetic compass as I'm flying west of the agonic line. In which cardinal direction is my magnetic compass pointing? for the most part. What would you guys say in that example? My aircraft is pointing north.
East.
Yeah, east, right? It naturally swung over to the east because it wants to point to that magnetic North Pole. So we call this an easterly variation. Let's look at this example over here. I'm flying east of the agonic line. Look at what happens to my magnetic compass. My aircraft again is pointing to true north, but my compass naturally swings to the west. And we call that a westerly variation. So you can see that there's a need in this example right here. If I truly want to fly to the true North Pole and I want my magnetic compass to have the correct reading, I'm going to have to compensate for that. I'm going to have to track a different magnetic course than the true course. Okay, and we do that by remembering this little phrase here, and my flyers are going to be very familiar with this. Okay, it's east is least, west is best. And I'm going to give you an example here to hopefully make sense of all of this material, because I realize that it's a lot. And that's why we teach this and go immediately to a break. Okay, so here's the example. Again, remember, east is least, west is best. And what this is referring to, it's asking, okay, where is your aircraft in relation to this agonic line? Okay, I'm over here to the west. What happens to my magnetic compass when I'm flying over here west of the agonic line? Well, my needle wants to point to the east, so I have an easterly variation, versus the example where we're flying east of the agonic line. My magnetic compass wants to point to the west. We call it a westerly variation. Okay, so here's our example. We've drawn this red line representing your course to be flown from point A to point B. And this is a no wind scenario, okay? My true course, this red line, is a 080 degree true course. And if you look at my aircraft's heading, the nose of my airplane, that aircraft is also heading in the same direction. There's no wind in this scenario. So my true course and my aircraft's true heading are the same in this scenario. But there's a problem. And I'm going to ask Chris. Chris, how often do you use a true heading when you're flying the aircraft?
I guess if you lose GPS and all your instruments and you're dead reckoning, that's about the only time.
That's probably the only time, right? A true heading is useless to Pete and to Chris. They really do not care about a true heading. These guys want a magnetic heading because they're using a magnetic compass. So how do we get there? Well, we know what the true heading is, 080 degrees. And if I look on my aeronautical chart, that's what we call the fancy maps in aviation, aeronautical charts. We'll find a line or an isogonic line running through my course. And in this example, it says -10. Okay. It's really going to be listed as a 10E. Okay. 10 east, meaning it's an easterly variation, isogonic line. What this tells me is east is least, west is best. So if I have a 10E, that tells me that I have to subtract, in this example, 10 degrees from this 80 degrees to get a magnetic heading of 070 degrees. And this is what our pilots want, right? In the end, they want to know, what is my heading in magnetic so that I can stay on this course of 080 degrees. So whenever you're trying to convert a true value to a magnetic value, you need to think east is least, west is best. Okay, again, going from true to magnetic, east is least, west is best. And I'm going to ruin it for you right now to tell you that SkyVector will take all of this into account for you, and it will actually determine what your magnetic value is going to be. So, okay. Fortunately for you, this isn't something that you're going to have to do all that often. But do remember that little saying, east is least, west is best. Now, I want to show you guys what these isogonic lines look like on the aeronautical charts. And that's the next slide here. Okay. There are two main charts that pilots look at and refer to when they're flying, depending on the type of flying that they're doing. Okay. If I have pilots out there that are just using visual reference, they're looking outside to fly, they're going to be referring to what we call a VFR, or a visual flight rule sectional chart. Okay. And then this is another chart over here, this white one. This is the one that you will eventually become really familiar with. And while you're with me, we're going to actually go through what this chart is. But this one on the right-hand side is an IFR chart, an instrument flight rule sectional chart, or an en route chart. Okay. And you'll notice that the isogonic lines are depicted on both of these aeronautical charts. A little differently in each, but they're still showing the same information. So you have a dashed magenta line here with a 9 degrees east. And then over here in the same area, just a different chart type, you have a thin green line with, again, 9 degrees east. This tells me that this is an easterly variation, meaning that my magnetic compass is wanting to swing to the east. That must mean that this is somewhere west of the agonic line, or that line where there's no difference between magnetic north and true north. So when pilots see 9 east, or individuals that are planning the flight, in order for them to go from a true course to get a magnetic course, they know that they need to subtract 9 degrees from the true course. Okay, and by subtracting that, that's what gives them, again, the magnetic value to give to the individuals using the magnetic compass in the cockpit. Okay, so when converting from true to magnetic, we say east is least, west is best. And so whenever I draw a line, if I were to draw a line on this chart here, see if I can do it. Okay, because my map is oriented using the longitude lines and latitude lines that are oriented with true north, any line that I draw here is going to be a true course. Okay, does anybody not understand that part? Okay. If that doesn't make sense, let me know. Again, you see the lines of latitude and longitude here. And for that reason, that's how my map is oriented. It's on that. So if I draw any lines representing a course, whatever I've drawn is a true course value. And a true course, again, is not helpful to a pilot. They want to know what the magnetic value is. So we have to look here for that magnetic variation, or that difference. If I see an east here, then I know I need to subtract so many degrees from this true course. Or if it were a W, 9 degrees W, I know that I need to add a certain number of degrees to convert it to a magnetic value. Okay. Well, with that, are there any questions, you guys, regarding what we've talked about up to this point? Latin longs, a true course versus a true heading, right? Taking into account wind. And then also knowing that we have to sometimes convert a true value to a magnetic value, and we're taking into account the magnetic variation. Okay. All right. Well, then with that, let's go ahead and give everybody 10 minutes. I do ask that everybody please raise your hand when you step away. That way I can tell who's not at their desk and who's come back. So we'll put 10 minutes on there. Let's have you be back. Let's do 40 minutes past the hour. And I'll put a little timer here at the top for 10 minutes. All right, guys, let's get started. Go ahead and lower those hands and we'll pick back up where we left off. Okay. All right. So I mentioned earlier before the break that pilots, dispatchers in the aviation world, we use these maps, which we don't refer to them as maps. Okay. We refer to them as aeronautical charts. And there are 2 aeronautical charts that you need to become familiar with. The number one, or the first one we're going to talk about, is the VFR sectional chart. Okay, and we're just going to talk about it very briefly today. Same with the IFR en route chart. So the VFR stands for Visual Flight Rules, and IFR stands for Instrument Flight Rules. So there's one aeronautical chart that is used when flying visually versus the other one, you're using the instruments to navigate from point A to point B. Okay. Now, the VFR sectional chart will not be used in this class. All right. We are concerned as dispatchers, dispatching flights under FAR Part 121. We dispatch them under IFR rules using the instruments. So we're going to be using and should become more familiar with the IFR en route charts. The VFR charts are helpful to kind of get an idea of the terrain and the things that are out there in that area. It enhances your situational awareness a little bit. But if I zoom into this chart, I can kind of show you what's included on it. Okay, you have airports, obviously, are included. Different types of airports. We've got these different circles and different colors. This magenta color, this blue dashed line. These are representing the different classifications of airspace out there, which we could spend hours talking about just that alone. You can see lakes. Yeah, that's not right. You can see lakes over here. You've got different obstacles, these little teepee looking things. Looks like a teepee with a dot. That's an obstacle. You have antennas over here. So as you can imagine, I mean, we just said that this kind of aeronautical chart is used by pilots that are flying visually, right? Using their eyes. Versus this chart over here, the IFR en route chart. This is still going to depict certain classifications of airspace because there's rules associated with all of that in flying, but it's primarily going to stick to just showing like where the airports are located. Like I said, sometimes airspace boundaries will be depicted depending on the type of airspace. You have different air traffic control centers and different military areas that will be highlighted on these charts. Most importantly, you're going to see these different nav aids, which we're going to go into today. And these solid black lines, you can think of these as the freeways in the sky. Okay, these are the roadways in the sky. And we're going to go in and I'm going to teach you about these freeways in the skies until you're sick and tired of it. But we'll get into that a little bit more. Betty, do you remember all this? Yeah. When your internet was working, right?
No, it's quite different from last time. This is much better than last time, I think.
Good.
I mean,
Good.
last time,
Good.
yeah.
Awesome. All right. Now I got to ask a question to Pete. You were CHP, right? You were flying around. You're a big VFR guy. So it's interesting, you guys, to see the different roles of our pilots, right? Pete was in a role flying, but he did things in a much more visual environment. Whereas help me out here. Chris, right? You did a lot of IFR flying, did you not? Or am I mistaken?
Yeah, we did. I mean, we followed IFR pretty much all the time, unless we did a lot of low level flying. So we did a ton of VFR stuff. We used to have to go and hand draw all the changes to each obstacle along our route of flight, 5 miles either side, stuff like that. Yeah, it was super fun. That's why VFR sectionals give me a nightmare.
Exactly. So, yeah, and then thinking about Pete flying around in Northern California area, there's a lot going on there. So, I'm sure those guys, the flying community is very much familiar with these two different aeronautical charts. And so the faster you guys can become familiar with what's on these charts, the better. Again, because you only have a limited amount of time to learn everything, I just want to reemphasize that we're going to focus mostly on the IFR en route charts. And the IFR en route charts have these two different types. You have your low en route chart, and you have a high IFR en route chart. So low and high, and it's all based on the altitude that you're operating in. Okay, but for the most part, it's all the same information that you're getting. You're still displaying the freeways and the skies on both. And I'm going to take the time tomorrow. We're going to actually go into more detail as to what really am I looking at with all of this that's being displayed to me right now in front of me. What do I need to know about what I'm seeing here? Because there's a lot, right? You got a lot of numbers, a lot of lines, a lot of different symbols that don't make sense. I'm going to help you guys tomorrow make sense of what you are seeing on these aeronautical charts for a beginner, okay, to get you guys started and to make it more pertinent to you as a dispatcher and not necessarily a pilot, okay? So again, for right now, just know that aeronautical charts are used by dispatchers. We use the IFR en route low and the IFR en route high, and these simply display the different airports and the different freeways out there in the sky that the pilots and that dispatchers can plan and ultimately a pilot can fly on. Okay, we'll just start there. Any questions up to that point regarding the freeways and the skies? And like I said, this group has the most pilots in it, so that's pretty cool. Brian, let's go with your question.
Okay, so this isn't necessarily just specific to the freeways in the skies, but I just want to make sure I'm thinking. I think this is probably silly, but I just want to make sure I'm thinking about this correct.
Yeah.
So on our charts, everything is in true, based on true north, right? With the exception of those lines that you showed earlier where it shows set. So that when we're as dispatchers, when we're creating the flight plans, we take into account those offsets. So we basically convert all the headings and everything to magnetic north, right? Based on the offsets.
No, you actually won't, because everything's going to be digital when you get to the airlines. So it's going to do it automatically for you. The only time you have to convert true to magnetic is when you're actually taking a pencil to a paper.
Okay. Yeah. So that's what I guess so me or the software is the one that's doing the conversion. So I guess my question is I just want to make sure. So when that pilot's in the cockpit, and obviously if he's got a physical compass, it's obviously going to be magnetic, but I'm assuming any digital displays with direction, and that's all magnetic as well, right?
You got it.
So so when he has that flight plan and everything, it's all based on magnetic north. It's just the conversions have already been made as part of creating the flight plan. Is that correct? Okay.
Yep.
I just wanted to make sure I got it.
You got it. And I'm just going to throw this out there because you asked. For those of you who are not going to understand what I'm going to say next, don't worry, because we're going to spend more time on it later. But this little thing right here is called a nav aid. It's a component, and specifically it's a VOR, or a VORTAC. It's a very high frequency omnidirectional range. It's a component on the ground that sends out a signal, okay? And pilots will fly to it and then navigate off of that component. I just want to show you something. This line right here on the map is the longitudinal line, right? A true line. I'm really talking to Brian because you were asking this question. This is a true line, a longitude line. Well, this navade here, do you see how it has this line that kind of veers off to the northeast a little bit? The reason for that is because these navades, these ground-based components, are actually oriented to magnetic north, because pilots are going to be flying to them and from them. They're already calibrated and oriented to magnetic north. That's why this line here is pointing to magnetic north and not this way, parallel with this true latitude line. So what I'm saying is that all these lines, these freeways in the skies coming off of these different facilities or navades, are already oriented and developed and designed to be on a magnetic trajectory, because they know that the pilots are using magnetic compasses. So, but the cool thing is, Brian, is you guys are going to be in such an automated environment that you really don't need to worry too much about converting from true to magnetic. But it is good to understand and have that background in the back of your pocket to go, my map, the physical map itself was designed off of true core, true north. And any line I draw on that is naturally going to be a true course. And therefore I have to convert that and look at the magnetic variation lines. That's the old school way of doing things. But fortunately, we're learning dispatch during an age where it's very highly automated. We have programs like SkyVector that will already take all of that into account for us. So very rarely will you ever have to remember east is least, west is best to convert from a true course to a magnetic course. But, we're aviation professionals and we got to kind of know the why behind things sometimes. But, it's going to take time too to really, you're going to actually have to apply this to remember that. But, do the best you can. But I wouldn't say that concept's a make it or break it kind of concept. So don't get too discouraged on that one. But
real quick, how often are these charts updated?
Too often. No. They are periodically looked at and reviewed. We have a whole team that we do just that, periodic reviews, where you're given a section of the freeway in the sky to look at and to evaluate for obstacles. And so it's done often.
So when they're updated, they take into account any variations that have happened to magnetic north since the last one?
Absolutely. Yes.
Okay.
And there's tolerances to how far those differences can be.
Okay. All right. Thanks.
You bet. But yeah.
Is it still on a 2-month cycle? And then like a 1 month for digital publications or thereabouts?
Yeah, well, kind of, yes. For approaches, it's every 2 years it gets a partial, and every 4 years it gets a full review, where the specialist has to build the entire procedure and look for any new obstacles that might present themselves.
Okay.
So yeah, with these, it's about the same. It's every 2 to 4 years you're looking at everything, and that's actually not a lot of time considering how much of the NAS has to be looked at.
Okay, because we get database updates like 3 months, I think.
Yeah,
At least every 2 months.
Yep, and what happens is that's for the overall region. So it may not include like this Victor 1.7 being a part of that though. It's
That's what I was
just,
saying, yeah, because you're very myopic and you're thinking you're looking at like one approach, and in 2 years I have to rebuild this thing. I got you.
yeah, exactly. So for those of you with no aviation experience, really what I want you to take away right now is that we use the beginning of you flight planning begins here. You're told you need a flight from, say, Denver to San Francisco. Well, you're going to be using these IFR en route low and high charts to determine what freeways in the skies you're going to use to connect those 2 points, Denver and San Francisco. Okay, and they're going to show you how to do that next week. It's pretty cool. But just remember, the IFR en route chart has the freeways in the skies that you need to determine, okay, I'm leaving this airport, I'm going to get on this freeway, and you're going to ride that freeway until you need to get off at the exit. And they're going to show you how to do all that. Okay. So a big part of the navigation is understanding basic navigation calculations. Nothing too cosmic here, you guys, okay? But you do need to be able to understand that we have to convert minutes into equivalent hours. There may be a need to determine a distance. Your ground speed, how fast you're traveling over the ground, the time it takes for you to fly a specific distance. And also, you have to sometimes calculate, this is all basic calculations, but calculate your fuel consumption. And that can be either as gallons per hour or pounds per hour. And your higher performance aircraft, like the CRJ 700, is going to use pounds per hour, okay, versus your gallons per hour. Now I'm going to reach out here and I'm trying to remember. Does anybody remember the pounds per hour that the CRJ 700 burns? I know you guys have talked about that. How many pounds of fuel does the CRJ 700, Chris, burn per hour?
They said they're using 4,000 for the first hour and then 3,000 in cruise for their planning.
Yep, that's correct. Yep, 4,000 pounds an hour. So as we go through some of these different calculations here, you guys, I want you to know that during the in-person portion of your training, you're going to be given a lot of these known variables. Okay, there's going to be a lot of known variables, and you just have to figure out which variables to use, especially during the fuel consumption calculations. Use the variables that have been given to you, and it will make your calculations a lot easier. So I see a lot of students go, oh my gosh, the fuel consumption calculation, this is too much. Well, there's already going to be a lot of knowns, a lot of things that you'll be given. So use that to your advantage. Okay, so just keep that in mind as you start moving forward here. Let's look at a couple of these. Converting minutes to equivalent hours. Again, remember, you're going to get these slides, but minutes to hours. How do you do that? Well, you're going to divide by 60 because there are 60 minutes in 1 hour. So if you need to convert 30 minutes into hours, you take 30 minutes divided by the 60 to get 0.5. For hours to minutes, you'll multiply by 60. So if you have 0.75 hours, okay, you multiply that by 60, you get 45 minutes. So you're just able to convert minutes to hours and hours to minutes. And this is how you do that. For your distance, well, your distance is going to be your ground speed multiplied by the time that you spend at that speed. Okay, that'll tell you your distance over the ground. So here's an example. The distance flown in 1 hour and 45 minutes. So we know how long we spent flying. How fast did we go? 120 knots. we went 210 nautical miles. So it was 120 for the speed multiplied by the time that was spent doing that, 1.75. And we know that we've gone 210 nautical miles. Ground speed. If you know your distance and your time, you just divide those two. So an aircraft flies 270 nautical miles in 3 hours. What was your ground speed? So you know that you've covered this distance in this amount of time. So if you divide that together, you get 90 knots. So we're talking about a smaller aircraft here. And time is equal to your distance divided by the ground speed. So the time to fly 210 nautical miles, that's your distance, at a ground speed of 140 knots. That tells us that it took us an hour and a half, 1.5 hours, to fly that distance at that ground speed. And then your fuel consumption, like I said, this is a big part of dispatch, right? Understanding and determining how much fuel is needed. In the airlines, once you get to the automated portion, right, the computer's going to tell you. But during your practical and everything, you got to really have a good understanding of how this is calculated. And during the in-person portion, you're going to have many opportunities of planning different flights and taking all of this into account. So again, I'm just the messenger, Al, right? Just trying to introduce this to you. So for the fuel consumption, you got to have a route distance. So you got to know what your route is. I know that I'm going from Denver to San Francisco, but I first have to determine what my route is so I can calculate the distance from point A to point B. Once I know that, then I have to take into account winds. And you guys have looked at the winds aloft chart, right? To see what the wind direction and speed is at different altitudes. If you haven't, you'll have more opportunities and experience with that during the in-person. You're also looking at your fuel consumption. Again, for the CRJ 700, you guys know about the pounds per hour to use. That's a known variable. And the ground speed. Okay, that's something else that will be given to you in your flight plan packet when you start flight planning in class. And then you'll be able to determine how much fuel is needed to complete your route. And you have to keep in mind that there's all those different FARs, those regulations, right? You need enough fuel to reach your destination, then to the most distant alternate, and an additional 45 minutes at normal cruising speed. All of these FARs and all these regulations are going to start coming into play here when you start planning your flights in practice in class. So here's an example. We have an aircraft that travels 400 nautical miles, and these are all simplified, right, you guys? We're not going too crazy here. You have an aircraft traveling 400 nautical miles at 100 knots ground speed. And we know that this little aircraft consumes 5 gallons of fuel per hour. So how much fuel is needed to reach the destination? There's no wind here. Okay. So we know the distance was 400 nautical miles and that we're traveling 100 knots over the ground per hour. So we just divided the distance over the ground speed to get 4 hours. And we know the fuel consumption of my aircraft is 5 gallons of fuel for every hour. So we're flying for 5 hours. It eats up 5 gallons of fuel per hour. So we get 20 gallons of fuel is going to be used to fly from point A to point B there, that 400 nautical miles. Okay. So again, basic calculations that you're just going to become familiar with. They're going to go into more detail in class, more specific to the CRJ 700. But just keep in mind, I've got to build a route. I got to determine the distance for that route, take into account the winds so I can figure out how much time I'm going to be, how long am I going to be flying based on this ground speed. And then I need to know how much fuel is my aircraft going to use and consume. And by knowing all of those different variables, you're going to be able to determine how much fuel you need to complete that flight from Denver to San Francisco. Any questions, you guys, with regards to these basic navigation calculations? Okay. All right, let's get into some fun stuff here. Types of navigation. So long ago, people used to travel across the country following these cement arrows at different points along their route. And they also had these beacons as well at that location. That was the original system and the original way to, again, travel from point to point. And yeah, way back when, 1926, a company by the name of Western Air Express made the first regularly scheduled flight from Salt Lake City, Utah to Los Angeles, California. And so throughout Utah and out to California there are these different monuments out there. So for those of you going to the in-person portion of your training, you guys can still visit today these cement arrows out there. And I think there's 3, if I'm not mistaken, in St. George. I lived there for a number of years. My wife is from there. We've had multiple kids in St. George, and I can't believe I haven't been out to one of these sites. So when you guys are there, if you're looking for something to do before class, maybe go check one of those out. I've heard it's kind of a fun little hike in those different regions there. So, but yeah, that was the old way of navigating. Just you see the arrow, you go into the direction that the arrow is pointing, and you try to find the next arrow with the light, right? Not a very efficient way of navigating, if you ask me. We moved from that to taking advantage of radio frequencies and allowing aircraft to receive those signals and to provide instrumentation in the aircraft to fly from point A to point B. And that's that was a huge advancement. You didn't completely rely on having to see the ground to navigate from point A to point B. You're able to tune into these different radio frequencies and navigate that way throughout the NAS, throughout the airspace, which is pretty cool. So there's always been these advancements. And then we've introduced now, GPS, and we'll talk about that. But things have just continued to advance and to improve and to become more reliable, with the system that we have and that's in use today. So this is a really important section, you guys, that I definitely want you guys to focus on. It's important to understand the components and the different facilities and equipment that is being used on the ground specifically. This is where we're going to start, but also satellite-based components that help us, again, navigate throughout the national airspace system. As a dispatcher, if some of these things break and don't work or function like they should, it could cause your minimums to be higher than what you would expect. And that matters to you as a dispatcher because that will ultimately determine whether or not you are legal to go in those legal to go scenarios. So again, having an understanding of these different components is important. You're going to come across some of these components in a NOTAM or a notice to airmen, right? Notifying you that these components are either not working at all or that they have limitations, and you need to be able to understand how those limitations impact you. So I'm going to spend some time now and help you guys understand first some of the ground-based components that are used to help navigate. And then we'll also move in towards the end of our class today with regards to the satellite-based or the GPS-dependent systems out there. Okay, so first one we'll do ground-based. So with ground-based, we're going to talk about NDBs or non-directional beacons. Then we'll discuss the VOR, the very high frequency omnidirectional range, the distance measuring equipment, and also another type of navigation called the instrument landing system, or the ILS. Excuse me, guys, I'm getting over a cold. And the ILS is comprised of two different components, a localizer and a glide slope. We'll go into that here in a moment. Just fix my mouse here, it keeps disappearing. I am going to just make sure and just say this to the class. Please make sure that you're not writing too many notes down if you are. Sometimes I feel like if you're spending too much time on your notes, you're missing out on just letting everything soak in from the slide and from my explanations. So, you know, have a good balance if you can between taking notes and listening and watching on the slide. Sometimes I feel like, yeah, again, notes can kind of take away from that ability to comprehend what's being taught. And these topics can get a little confusing. Also, the other thing is, again, you're not going to understand this entirely the very first time. So take in what you can and remember that there are going to be other opportunities for you to build upon what you learned here in another class. So don't get too overwhelmed. Is there, Christopher, did you have a comment? Or I'm sorry, Chris, a comment?
Yeah. So I noticed on the week 4 study guide, it's all weather and no navigation. Is that by design?
For this class, yeah, we're not going to go into weather today.
No, I mean, we have a week 4 study guide and there's no navigation questions on it.
Oh, yes. You'll get that, I believe, next week. Yeah. Yeah, because you guys don't have your week 5 out yet, right? You don't have access to that?
Not that I've seen.
Yeah. I'll ask Jaden, but yeah, I don't think you guys get that until next week.
I think it's in the Google Classroom. I was going to try to print it to work on it while we were doing other stuff.
Yeah, and that is okay. That's a good point, Chris. Yeah, definitely get your weekly study guide, and I will let Jaden know. I'll take note of that to make sure that you guys do have access to that now, because that will kind of hone in on really what you need to know. Yeah, study guide. Yeah, thanks, Chris, for mentioning that. Cool. All right, so let's talk about these. The one out of all of these, the two that I really want to focus on with you guys and to kind of help you really understand, it's going to be the VOR and the ILS. So just kind of wait until we get to those two. That's really where I need you to focus and ask questions if you have any. So the NDB, this is an old school component, okay, an old school nav aid. The NDB is really what replaced the lit arrow system that we just got done talking about with the cement arrows, okay, on the ground. It really is the most basic of all of the radio navigation. It transmits a signal in all directions, and this signal does not have to be within line of sight. It can penetrate through buildings and other objects. Okay, and it has a 3-letter identifier. And here, I'm going to go to the next slide here and kind of show you how this is depicted on an IFR en route chart. Okay, this is an NDB symbol. As you can see, there's a center circle and then a bunch of little dots around it. That's indicating that it's transmitting a signal in all directions. It's omnidirectional. Okay, it's just broadcasting it out. And what the pilot does is they can look at this 3-digit number here, 370. They can type that in. So this one says 250, but they can change it to 370. And they can tune in to that NDB. And they have what's called an ADF, an automatic direction finder. Not important for you to remember, but it's this right here. And this is just a glorified compass. It's just all it's doing is it's listening or it's tuning into that frequency. And this yellow arrow here is going to immediately point into the direction of where that NDB is located. And so just like you as a kid, I always explain it this way in my class, where you're 8 years old and you're having fun with a magnetic compass around your neck in the backyard, and you're moving around and that needle's moving left and right. Well, imagine if your treasure box had the ability to send out a signal when you were a kid, and you're looking at your magnetic compass, and your magnetic compass immediately turns to where you need to go. And you just turn your body and start heading to wherever that needle is pointing. Same thing with this ADF. You tune into the frequency. This yellow needle will automatically swing to wherever that NDB is located, and the aircraft can be turned to that direction to fly to or from that nav aid. But it's simply just sending out a signal and you're flying to it. Okay. Not a lot is happening nowadays with an NDB. There have been a lot of opportunities to get rid of them where they're not needed, right? It costs money to maintain these items. So yeah, whenever there's an opportunity to get rid of an NDB or one's not needed anymore, they are being removed from the system from time to time.
If there's an opportunity for me to go blow one up, I'd love to have that opportunity.
You would love it. Good.
Put in chat what it's like flying an NDB approach. I put it in chat.
Yeah, I've amended and done a lot with a number of different NDB approaches, and they're not even fun to amend or maintain. They're an annoyance. That's for sure. So yeah, I don't even think, let's see, Caitlin, have you even, during your flight time, did you ever fly NDB?
They had us practice it just like a little bit.
Did you? Okay.
But not much.
Not a lot, huh? No. So,
that Stranger Things reference was really funny though, that Chris put in the chat.
Oh, see, sometimes I can't see that fun stuff. Oh yeah. Stranger, yep. Oh yeah. Good stuff. Good stuff. All right. So the next one, guys, probably the most important nav aid, okay, is the VOR. The VOR, again, stands for very high frequency omnidirectional range. I don't think you're tested on knowing the full name, all right? But you do need to understand the VOR, what the 3 different variances are of a VOR, and simply how they work, okay? I'm going to provide you with the best introduction to VORs that I possibly can, but it wouldn't hurt if you guys go, right, on your own time and try and research a little bit more about the VORs, how they work, how do pilots use them, right? The more that you guys can go and do some self-study on these topics, the better off you'll be, because again, there's only so much time allotted to me to teach you this material. And there's a lot to teach. Okay, so again, this is an item that you do need to know, the VOR. So like I said, there are 3 different types, and I'm going to explain what those 3 different types are and what the differences are between them. I also want to highlight right now that the VORTAC, this specific type of a VOR, is the one that is used mostly to create our freeways in the skies. Okay, our freeways in the skies are connected between a lot of different vortex. Again, a vortex is just a variant of a VOR, but that is important to know. The majority of our airspace system and the freeways in the skies are made up of the vortex. And there's a reason for that. And we'll get there in just a minute. So the first variant is a simple VOR. Nothing else but a VOR. This VOR is a much better system than an NDB. Okay. This one provides 360 degrees worth of radials. You can think of this as a bicycle wheel, right? With all the different spokes on a bicycle wheel. Same exact thing here. Okay. This is a system that is transmitting 360 degrees worth of radials. Radials radiate out from a center point, and the VOR component is right here where my mouse is at. The thing with the VOR is that the signal cannot penetrate the ground, mountains, buildings, okay? This, unfortunately, has to be used within line of sight. Okay, the aircraft has to be able to receive that signal. And all VOR types are given a 3-letter identifier. Okay, I'll go to the next slide here just to show you what that looks like and go back. But here's that IFR en route chart again. Here's a VOR, and there's a tag, and it tells you what the name is of that VOR with a frequency. And the pilots will tune in to that frequency, and then their instrumentation is going to pick up that signal and then display the information that they need to continue navigating using that navigation or that VOR. Okay. Going back to this, again, I want you guys to, let's zoom into this little image here. We have those 360-degree radials, which are also referred to as an azimuth. Okay, these radials are also referred to as an azimuth. And you can see here this blue line from the center point out in this direction is showing the 135-degree radial. So think of it as a compass, right? North is 0 or 360. East is 090 degrees. South is 180. West is 270. So you've got all of these radials radiating out. And this one specifically is the 135 radial. And then if I were to radiate out in this direction, this is the 315 radial. So everything starts from the center and then radiates out with a new radial. Think of like a tire spoke, right? If I'm at the hub of my wheel on a bike, and you can move your finger along that spoke to the rim, that is one spoke. In order to continue, you have to go over the hub, grab onto the next spoke, and go down. That's how you can think of the radials on a VOR. The other thing I want to mention is this airplane, this aircraft here, its nose is pointed in a completely opposite direction of the radial. So this aircraft is on the 315 radial, but it has a completely different heading, and that's fine. That is perfectly fine. But I know, regardless of the direction my nose is pointing, my aircraft is on the 315 radial. And our aircrafts can be flying on a radial to the station, and they can also fly from the station. Okay. Now, regardless of me flying to the station or from the station here on this example, I'm on the 135 radial. Okay. Regardless if I'm going away from the station or to it, I'm on that 135 radial until I get on the other side, right? Now, if I'm flying away from the station, I'm on the 315 radial, but I could also be over here flying to the station, and I'm still on the 315 radial. Any questions with that? Does that make sense to everybody? If not, that's fine. Speak up. Good. Good. So that's a VOR. All it does is it sends out 360 degrees of radials, or another term is azimuth. That's all it does. Okay. Let's talk about the next variant. The next variant. Oh, actually, let me share this with you. This you don't really need to know, but this is interesting. I thought it was, so we put it in here. The VOR, when it sends out its signals, okay, what it's doing is you've got this blue sweep that's sweeping around. This is the VOR in the center. It sweeps around 30 times per second. So it's spinning fast. And every time that sweep goes to magnetic north, right there, you see that green pulse, right? That green signal being sent out in all directions. When that happens, the aircraft receives that green signal, and then it waits to receive that blue sweep again. And theoretically, the time between the aircraft receiving that green pulsating signal and the time it takes to receive that blue sweeping signal, that will correlate into number of degrees. So it's able to determine that the aircraft in this example is on the 105 radial. See, it's radiating out from the VOR. That's how it determines what radial you're on. So that's just kind of an interesting tidbit to know, that these VORs are sending out an omnidirectional pulse and then a sweeping signal. And it's just using the difference in time that it takes to receive those two signals to correlate that into a degree. Okay. So we thought that was interesting. All right, the second variant, right? So the first one was a VOR. All it did was send out 360 degree radials. The second variant is a VOR DME. So this does exactly the same thing as a VOR, but we're also introducing what's called a DME, a distance measuring equipment. So now, I'm going to use the picture here. Here's my VOR DME, and here's my radial right here. Does anybody want to take a guess of what radial this is? If we're going in this direction, what radial would that be?
248.
What's that?
248.
248. Exactly. It says right there, 248. Yep. Now, with a VOR, we know that we can fly on any of those 360 degree radials, and that's great. But it would be nice to know precisely where I'm at along that radial, wouldn't it? That would be nice. I know that I'm on the radial, but I want to know precisely where I'm at along that freeway that I'm on. Well, that's where the DME portion of the component comes in handy, because now I can fly on the 248 radial going this direction on this freeway called the Victor or the V190 freeway. I can fly that until I'm 10 DME away from this component here, because it says 10. When the instrumentation shows that I'm 10 nautical miles or 10 DME away from this VOR DME, I've made it to this point, this triangle, or what we call a fix. Okay, this is just a point in space. And every point in space in aviation is given a 5-letter identifier. It's a name. This one is JITMA. Okay. And I know that I'm on this 248 radial and I'm waiting until I get to 10 DME away from here. I've reached JITMA. And there are a number of different things that can happen at JITMA. Okay, but the important thing is right now for you is to know a VOR DME is phenomenal. You can fly on any radial, and then you can also determine your position along that radial because it has DME, or distance measuring equipment. And how does DME work? Well, you have a couple different pulses that are being sent out. One is being sent out by the aircraft, and then there's another one being sent out by the DME component back to the aircraft. And again, the aircraft's equipment is able to interpret how long it's taking for the aircraft to receive a signal or send a signal and then receive a signal, and it translates that into a time or a distance, depending on the time it takes for all of that to happen. And this is what it kind of looks like displayed in an aircraft. Again, aircraft is sending out a signal. It's then receiving a signal from the DME component. And then it's able to translate that into a distance and display that somewhere in the aircraft's cockpit, right into the displays for the pilots. Now, because of the signal being sent out to the DME station and the reply pulse back to the aircraft is on a slant, your DME distance will always be greater than the distance, the actual distance over the ground. It's just trigonometry, okay? Your adjacent side here of the right triangle is always going to be less than your hypotenuse side. Okay, but it's called a slant range distance. And again, just knowing that the aircraft DME display is going to read a higher value than that over the ground. And it's just because of the way that it's being sent out on a slant. Okay, but that's VOR DME. So we have VOR 360-degree radials. We have the VOR DME, which still has the 360-degree radials, but it also has the distance measuring equipment capability. Brian.
So how does that slant distance work with the what was it, the fix there, the the point you were just showing on the chart?
Yep.
Like let's say 10. So wouldn't that be actual different point depending on what your altitude is?
No, it's going to read, it should let's see. This one's just going to be your 10 DME. So in the aircraft, Chris or Pete, I don't know what you guys see in the aircraft, if that's going to read a little bit more distance once you actually fly over it. It might be like what, 1/10 of a nautical mile difference. I don't know. when you're flying it, but I mean, if I go back here, your DME display in the aircraft is going to be greater than the actual distance over the ground because it's on a slant, the slant
That's correct.
distance. So, but again, I'm not a pilot. So Chris, I don't know if you guys on your DME distances that are not GPS DME, the old school DME.
Yeah, I haven't flown raw data for a long time, but yeah, it would be, it would show greater than what your actual distance was. So you'd have to take that into account.
Yep.
So is that
Especially if you
a,
get, oh, go ahead.
well, I was just gonna. So is that triangle? Is that a physical, like, item broadcasting something, or is it just a? I mean, or is it just a theoretical point in space?
It's just a point in space. I mean, it has a lat and long assigned to it. So when we create these fixes, they have a lat and long coordinate that are assigned to it. So they're an actual lat and long coordinate geographical point in space along that freeway in the sky that is based off of this navade oriented to magnetic north.
So would you have to, in your aircraft, depending on your elevation, would you have to kind of do the math to know once you've actually reached that JITMA?
Yeah, the pilot side I'm not too familiar with, but all I do know is that because it's being sent on this slant, your DME display is going to be greater than what it actually is over the ground. That's all I can give. I mean, unless we have other pilots that can give a different explanation. I don't know. But it is transmitted on a slant, and then it's that reply pulse from the DME station is also sent out on a slant. So that's where you get the difference in the DME display compared to what's on the ground. Now, a lot of pilots will say, I don't know, I just use the DME off of the GPS. And at that point, it's exact. It's not on a slant, right? So we're talking about like old school. This is the bottom of the barrel type of flying. People that they're using the very bare minimum in their aircraft, not all the GPS fancy stuff. So, which your aircraft and the airlines would be. But again, going back to the Stone Ages here, trying to go back to the very, very basics. Yep.
Typically, the air is negligible as long as you are the same amount of feet above the ground that you are miles away from the station. So
Yeah,
10
yeah.
DME, as long as you're 10,000 feet or below, the air will be negligible.
Yeah, there you go. Thank you. That's awesome. Yep. Perfect. Thank you. Who was that Brett? Couldn't
Yeah,
see who it
yeah.
was. That was Brett. Okay. Thank you, Brett. All right. So the third one before we go on our break, really quick, is the VORTAC. Okay. So we have VOR, VOR DME, and VORTAC. The VORTAC is going to act and provide the exact same information that the VOR DME gives us. It's just that the DME component is now coming from a military component called the TACAN, or the Tactical Air Navigation. So both the VOR and the TACAN provide an azimuth, or 360-degree radials, but the TACAN is going to provide these signals on a UHF, or an ultra high frequency, that is only going to be used by the military, versus our civilian aircraft using a VOR that transmits on a VHF, or a very high frequency, okay, component. So again, it sends out 360 degrees worth of radials. So for us civilians, that's good to know. And it also is able to give us distance measuring information because of the TACAN. The TACAN for a civilian is useful because it provides DME capabilities, and nothing else is useful to us as a civilian with the TACAN. So when you see VORTAC, you can think of this as another type of VOR DME. It's going to provide you with 360 degrees worth of radials, but it's also going to give us that distance measuring equipment information that we need so that we can determine our position along a radial. Okay. And again, as I mentioned earlier, the majority of the NAS and the freeways in the skies are made up of the VORTAC. Okay, the majority of them that you see out there are going to be either VOR DME, but primarily this version, the VORTAC. So before we go on break, do I have a volunteer who feels comfortable in just simply telling us what do we get from each of these three variances of a VOR? Again, the three are VOR, VOR DME, and VORTAC. Any takers? and then I'll give you 15 minutes. How about that? Who do we have here? Is it Lakeisha?
Yeah, I just want to go on break, so I'm going to give it a shot.
All right, I appreciate it.
So the VOR provides 360 degrees worth of radials or azimuth. I don't know how to say that.
Azimuth.
It cannot penetrate the ground or the buildings. It's only a line of sight direction. The VOR DME provides the same thing as the VOR, but with the distance measuring equipment.
Perfect.
And then the VORTAC provides both azimuth and distance information. I don't know what else from that one.
No, that's good. That's good. And that's all I really want you guys to know is that, again, the VOR sends out 360 degree radials. Oh, sorry, the pen's not working very well. And that's it. That's all you get from it, right? The radials. That's it. Now, the VOR DME, you also get those radials. Okay. But now you also have DME. Now you can determine where you are along any radial, okay, by using DME. Same thing with the VORTAC. You have 360 degrees worth of radials. And again, I can still determine where I am along one of these radials, and there's 360 of them, but I can determine my distance along that radial because of the TACAN. The TACAN is what gives me that distance measuring equipment information. So if the TACAN is nodemed out and it's not working, let's say the TACAN is out of service, what do I not have anymore? If the TACAN goes out,
DME.
What am I missing out on? DME. Yep, missing out on DME. Okay, and that will be a common NOTAM that you'll see. So keep that in mind. All right, you guys did really well. Sorry, that's a big section that we absolutely have to get through. It's a big deal. So let's go ahead and put you on break for 15 minutes. Let's have you be back at the top of the hour, please. Okay, we'll see you then. Please raise those hands. Thank you. All right, guys, welcome back from break. I know it's never long enough. I get it. But hopefully you guys were able to step away, grab a bite, grab something. But we're going to continue moving forward. Go ahead and lower those hands. Are there any questions? I mean, I know there are probably a ton of questions. I get it. There's a lot of material being thrown at you right now. But is there anything that needs to be immediately addressed, or is everybody good just to continue moving forward? Okay. All right. And again, lower those hands if you guys are back. Looks like we only have 2 away, so we'll unfortunately have to keep going. Hopefully they get back to their desk soon. So the next question is, okay, now that we know what a VOR is, and it has 3 different variances, how do we actually use the VOR? In what ways are they used? VORs are used to help identify fixes or geographical points in space. And again, those geographical points in space are given a 5-letter identifier, okay, a 5-letter name. And we'll look at that more in future classes. Actually, tomorrow we'll take a bigger dive into that. But we use VORs to help identify fixes in space, these different points. These different fixes, and everybody can see my screen, right? The types of navigation. Just wanting to make sure before I continue. Okay, good. All right, these different fixes can either be what we call an intersection fix, or they can also be referred to as a DME fix from time to time. Now, an intersection fix is going to require the use of 2 VORs. And I will just say right now that this is more informational, okay? Nothing that you actually absolutely need to remember, so just keep that in mind. But an intersection fix is simply that. It's where 2 radials, a radial from, say, this VOR1 and another radial from the second VOR, intersect each other. Okay, that's called an intersection fix. You have 1 radial off of this VOR that you fly on. Like you can see here, the aircraft is flying on this radial off of this VOR1, but it's also tuning into this VOR2 over here on a specific radial to help identify this point. So as the aircraft is flying on this radial and then it intersects this radial here, it knows that it has reached that fix. Now, with what you guys know about VORs and their radials, can anybody guess or just give me an estimated radial here for this VOR1, this radial that this aircraft is on? Any ideas? And there's no right answer, really. I just want to know if you guys get the gist of it.
Maybe about 110.
Yeah, let's do 110, right? Yeah, because if I were to go straight out, that would be 090 degrees. So yeah, let's just say 110. So the aircraft is flying on radial 110. And somebody give me a radial for this VOR2.
260.
260, perfect. So again, where X marks the spot, if you will, or where the along course radial and that crossing radial or reference radial intersects each other, that's where that fix is located. Now, I know you don't understand all the exact ways of using those radials in the cockpit, like from a pilot perspective, and that's okay. But I just hope you guys can see that using VORs and using more than just one VOR can help you determine where a fix is located. We also have, again, a DME fix. So with the DME fix, you don't need a second radial. right? Forget the second radial. You don't need it. You have DME, you have distance measuring equipment off of this VOR. So as your aircraft is flying on this 110 radial for 10 DME, that's just an example, right? Then we know that we're at this fix. So that's the great thing about DME, is that you don't need another VOR to help you figure out where you're at along a particular radial. Here's another use, okay, of a VOR. VORs are widely used on instrument approaches, okay? Now, for those of you who are new to aviation, this sheet here that you're looking at is what is used by our pilots to help them navigate to an airport when the visibility is less than perfect. So when you're flying in the clouds and you can't see and you're relying on your instruments, this chart here is helping our pilots understand what courses and what altitudes they need to maintain in order to avoid obstacles and safely make it to the airport. And I wanted to show you how we use VORs to accomplish that. Okay, and this is a fairly basic one here. Here is the VOR. What type of VOR is this? Does anybody know? Remember, there are the 3 different variances.
The Vortec.
That is a Vortec. Now, somebody tell me, what does this Vortec provide a pilot with? What information is available from it? What we talked about.
The 360 radial, and
Perfect.
then the TACAN gives them the DME.
Excellent. Perfect. Okay, so let's just assume that our pilot flies to this Will Rogers Vortec, and they fly this 355 radial, okay, outbound. See how they're flying away from the radial. This is the airport. Now, this particular approach is to this runway 18, so they'd be landing in the opposite direction. So they actually have to fly on this radial, the 335 radial. See up here, it says R335. That's indicating the radial that's radiating out of that VOR. And the pilots will fly that radial until they get to this fix called PULTZ, P-U-L-T-Z. Does anybody know how the pilot will know that they're over this fix, PULTZ, when they're on this radial? Any idea? I'm trying to zoom in as much as I can.
Would it be 20.7 miles from the
Yes.
Vortec?
Excellent. Yes. Yep. See, and it tells, if you look at that 20.7, it's inside of this D shape, and that's like the DME. And then it tells you where that DME source is coming from. It's coming from that IRW Vortec. So yeah, when they fly from the Vortec and they go 20.7 DME, and they see that, they've reached PULTZ. And what happens is the pilots will then know that they can fly outbound and turn to the left to 290 degrees, and then turn back inbound on a 110 degree to intercept that radial again. But this time, instead of flying away from the station, when they come back on this 110 heading, they're going to intercept that radial, but fly inbound now. And they're going to fly inbound towards the station again until they, in this case, they're going to land at this airport right here. But they're doing all of this using a VOR, and more specifically a Vortec, that has radials and DME information to help navigate along a radial and ultimately see the airport in sight to land. So it's a pretty remarkable document that helps our pilots stay clear of obstacles. They're able to use these different nav aids like the VOR to navigate without being able to clearly see outside of the cockpit window. Okay, so hopefully that was interesting to see how the VOR and their radials and DME are used to help to get or to help an aircraft get down and land at either an airport or a very specific runway, like in this instance. Any questions, you guys, on that? I know I think we have one hand raised, but I don't think they're back from their break. Or Brian, did you have a question? Oh,
Yeah.
yeah. Go ahead, Brian.
So when you're going outbound from the VOR and you pass that, you pass that pulse point, is there a certain amount of distance you need to keep going before you change your heading to 290?
I believe it's time. I think you do it for like a minute. You fly out for a minute. I could be, yeah, Sam, am I right? Okay. I got to rely on my pilots for that kind of stuff. Because when we design it, it's not based on that at all. So
that's not to scale then. It's just a matter of once you pass that, you go for a minute. And okay.
Yep. And just so you know, yeah, this little squiggly line here means just that, Brian. It means that this is not to scale. That's not
gotcha.
20.7. Okay. Yeah.
Cool.
Yeah. You bet. All right. So to continue with this VOR concept, the last thing that we need to cover with regards to the VOR is that, again, a reminder that the VOR is limited to line of sight. So if you're hiding behind a wall, it's not going to work, right? You got to be high enough and you got to be within range of this VOR to work, in terrain included. So got to be careful with that. It does have that limitation. The other thing to add and to mention is that, again, our VORs do not work at an unlimited distance away. So even though you may be within line of sight, if you're too far away or too high, these signals will either be degraded or not reachable or usable at all. So each VOR is given a classification or a service volume type. And each of these VOR types or service volume types will determine its strength and capability. And so there's a lot that goes into this, but as a dispatcher, we want you to know both the legacy service volumes and the new service volumes. So again, these are just ways that we have been able to classify these different nav aids or VORs to help us understand their strengths, right? So the legacy terms, and they're slowly switching over to these new terms. Again, lucky for you, you get to learn it while everything's being transitioned over to this new classification. But we're going to teach you both, and I'm going to tell you exactly what you need to know about this. But the legacy service volumes are the following. They're terminal, low, and high. And this you do need to know. Okay, legacy service volumes for a VOR, terminal, low, and high. The new service volume classifications are VL and VH, just those two. Okay, they stand for VOR low and VOR high. Let's take a minute to look at the legacy service volumes. Okay, the three here, T, L, and H, terminal, low, high. So what does this actually mean? Long story short, what we're saying here is that for a terminal VOR, This tells me that this VOR is going to only be good out to 25 nautical miles. For a low, it's good out to 40 nautical miles. And for the high, it's good out to a maximum of 130 nautical miles. So as a dispatcher, again, for the legacy service volumes, I want you to remember terminal, low, and high. Terminal, 25 nautical miles. Low, 40. And high, 130. For a pilot and a designer, there's a lot more that goes into it, but don't go down those rabbit holes as a dispatcher, okay? We just want you to simply remember these three types and these three nautical mile distances. That's for the legacy. And then for the new service volumes, for a VOR, they're classified as low and high, or VL, VH. The VL, what's happened is they've allowed that legacy low, instead of only being good out 40 nautical miles, they've said that it's now, if you're at the right altitude, it's good all the way out to 70 nautical miles. And for the VH, it's still good out to a maximum of 130. But what they've done is they've also added in between 5,000 and 14,500 above the station elevation, so above the VOR, they've said that it's good out to 70 nautical miles again. Okay, so for this one, I need you to remember VL, VH, VL out to 70, and VH is still 130. Okay, again, what does all of this mean? It's just helping you understand that depending on the service volume type of VOR that you're dealing with, will ultimately determine its strength and how far away or how high you can be from a VOR and it still work. Okay, it's the advertised strength of the VOR. And just make sure you don't get that confused with the three variances of a VOR, right? That's VOR, VOR DME, and VORTAC. But what we're saying is those types of VORs are then assigned to one of these either legacy or new service volume classifications, which then tells you its overall strength and power potential.
And where will we find that information? How will we know which one it is?
I'm going to show you right now. Very good question. You're asking really good. Was that Lakeisha? Thank you.
Yes, thanks.
All right. You bet. No. Making sure I'm going in the right direction. I like it. So when you, and we're going to look at this again tomorrow, but if you were to go to the IFR low and high en route charts, you're going to see that in parentheses, there's going to be either a T, L, or H, right, for the legacy. And that will tell you whether it's a terminal, low, or high. And let's see if these other ones, okay. This is from a Jeppesen chart, so a different type of publication, but the same information is provided. It's pointing to the VOR, the name of the VOR, the three-letter identifier, the Morse code, the lat and long coordinates, but in parentheses, you see here an L. This one has in parentheses an H, and that's telling you what the VOR service volume classification is. This is a high VOR, good out to 130 nautical miles. This is an L, good out to your, what do we say, 40 nautical miles for the legacy. Okay, and this D here just means that it has DME. Okay, so those are just two different publications. One's from the government, one's from Jeppesen. Okay, you guys feeling good about that? Okay, and don't think too much about it. I mean, don't start going, okay, well, what does this mean then? And how do I use, don't do that right now. Just take it for what it is. I know that there's 3 different types of VORs. And then I know that those 3 types of VORs are advertised with a certain strength, right? Either a legacy classification or a new classification. And I know that that correlates to how far out I can be based on those altitudes. But as a dispatcher, you're just worried about the distance. Okay. And I've been hearing more and more from current dispatchers that that's good information, but they're not even going to test you on it. But you, I will just say you will be tested on it for your week 5 test. So here in the class and in the course, we do need you to understand those concepts. Yep. There's a lot of things like that, right? Where the class is so much harder, and then you get into the real world and it's like, oh my gosh, it's a breath of fresh air. I don't have to worry about that. That happens. All right, let's move on to a different topic. I would consider this to be a little more exciting. The instrument landing system. And by a raise of hands, how many pilots out there do I have in the class that have actually flown an ILS procedure in using the localizer and glide slope? Cool, good, awesome. So that's great. Again, I've never had this many experienced pilots in a class. I like that. That's really awesome. All right, so the instrument landing system is going to be using components on the ground to provide vertical and lateral guidance to a runway. Okay, and the component that's providing the vertical guidance is called the glide slope. And the component on the ground providing the lateral left and right horizontal guidance is called the localizer. And you can see here, this is just a depiction of what we call a glass cockpit, right? It's a computerized display of both our glide slope, so helping me understand if I'm too high or too low. And also this green bar here tells me whether I'm centered on the runway or if I'm too far left or too far right of the course. So again, the ILS component is comprised of, this is really important to know, okay? An ILS system is comprised of a localizer, or abbreviated as the LOC, that's these antennas right here, okay? A glide slope, this antenna, this tower. We also have what's called marker beacons, not as important, I really wouldn't worry about that. And approach lights, okay, all the lights that you see here. The localizer is providing the lateral guidance, left and right. And the set of antennas that is providing that localizer guidance, or that left and right horizontal guidance, is going to be at the end of the runway, typically opposite of the direction that the aircraft is coming from, okay? It's receiving this signal from this set of antennas on the opposite end of the runway that is that the aircraft is approaching the runway at. So I mean, there are for those experienced people in the class, we know about back course approaches, right, where the aircraft is approaching and it flies over the antennas first, but we're not going to get into that today. For everybody, I just want you to know that the lateral guidance is coming from a localizer antenna that sits on the opposite side of where the aircraft is approaching. So that's why my aircraft is here, my runway's here, okay? And it's sending out a signal, and that's what it looks like. It's sending out 2 different frequencies. And this is just more informational, so you kind of know how this works. But that ground-based nav aid, that localizer antenna out here, is sending out a signal at a 90 hertz and 150 hertz frequency. And what's happening is the aircraft is receiving that signal. And if the aircraft is receiving more of that 150 hertz frequency, it's going to display to the pilot that the center line that they should be on is going to be over here to their left. So they're going to want to fly the aircraft towards that slanted line here so that they can get back on course. If it receives more of the 90 hertz frequency, then they're over here to the left. They need to go back to the right to get back on the center line. And again, this needle will swing left and right to display, and the pilots will chase that needle. They'll fly to that slanted line, and their goal is to get it in the center here of what we call the OBS. And this is a CDI, a course deviation indicator. Okay, but that's what they're trying to do. They're just trying to get that line to be vertical so that they are right down the center line as much as possible. And then you have a glide slope, okay, providing the vertical guidance, typically at a 3-degree glide slope. That is optimum. That's what every pilot wants to see, right? Is that 3 degrees. It makes for a very nice constant rate of descent. It's comfortable for everybody. It's not too steep and it's not too shallow. Okay, the glide slope antenna is going to sit off to the left or to the right of the runway, and it too is also sending out a signal out to the aircraft. And wouldn't you know it, it's the same two frequencies, a 90 hertz and a 150 hertz frequency. And again, if the pilot's getting more of the 90 than the 150, then there's going to be different indications for the pilots so that they know whether or not they need to climb to get onto the glide slope, so they're on that 3-degree descent, or do they need to descend down? Are they too high? Okay, and there's all those indications in the aircraft that will help them determine whether they need to descend or climb so that they are on the right glide slope down to the runway. And also the localizer tells them if they are aligned with the runway or not. Okay, so you've got that vertical guidance and that horizontal guidance. And when you have this kind of guidance, we call this a precision approach. You're being guided down both vertically and horizontally. And if you don't have that vertical guidance, it's called a non-precision approach, right? It's not as precise. So non-precision versus precision. I'm not going to spend a ton of time on this because this is a really old concept, but marker beacons. What can I say about the marker beacons? Well, the marker beacons, they are the system that was used prior to the development of DME. So we talked about how DME allows you to determine your location along a course, right? And you do that by looking at the distance from something. Well, before they had DME, they had something called a marker beacon. And basically, you just had these components along a course that whenever the aircraft would fly over it, you would get this flashing light, either an O, M, or I, along with some different sounds in the cockpit. And that would tell the pilot that, hey, you are at this point along your approach. Okay, it's called the outer marker, middle marker, and inner marker. You do not need to worry about this. We're not going to test you on this. Okay, here's an indication of the use of an outer marker on an approach. This is an ILS approach. You're flying on this solid black line from top to bottom of the page. The airport's right here where my mouse is at. So if I'm on this course flying from north to south and I have DME, I'm just going to be looking for 5.6. And that's coming from PWA, this VOR here. Okay, so when I get to 5.6 away from this VOR, then I know that I'm at this fix dirge. But if somebody doesn't have DME, they don't have that equipment on board, how are they going to determine that they're at this point? Well, in this instance, they can look for this blue light to flash in the sound to go off in the cockpit. As long as they're on this course and they see that light and that sound, then they know that they are at dirge and they can proceed with whatever else they need to do in the cockpit. So it's just a way of helping you identify your location along a course on an approach. But it's a very old way of doing it. Any experienced pilots out there have the opportunity to hear these sounds go off or see these lights?
All the time.
Yep, Chris has it. I'm sure, yeah, especially military, huh?
Yep.
Use them quite a bit. So cool. All right. The other thing that's important, this is especially important for the dispatcher side of things, okay? The approach lighting system, a big deal when we're talking about approaches. The approach lighting system is going to allow for a much lower visibility minima, okay? And if those lights are out, then you can expect your visibility minimums to be increased. Now, you guys have talked about legal to go. When you're talking about whether or not you are legal to go, the only thing you care about is visibility. It's the only thing, visibility. Let's take a look at this example here. We're going to talk about instrument approach plates tomorrow, but this is the very bottom portion of an instrument approach plate. This is where you determine what your minimums are for a particular runway or airport, right? This is where you're going to look. There will be times in an interview or in your training here at ADA where you're going to be sitting with an examiner, and I can almost guarantee you that you're going to get a NOTAM somewhere in your scenario that changes something that is, something that is normally a half statute mile is no longer a half statute mile visibility. And that's what we see here. We see here at Detroit, this runway 22 left, the approach lighting system is unserviceable or unusable during this time frame. So what does that mean? That runway 22 left on my approach, if I look at my landing minimums, I see that there are two sets of visibility minimums, whether I have functioning full approach lights or it says here, ALS is out. Look what happened to my visibility. I went from a half statute mile to now requiring 3/4 statute mile. So be aware of that. And if you're dealing with a weather scenario where the weather is really bad, and you really could use that half statute mile, well, if your approach lighting system is out, and this is the only procedure you have, then you've got to take into account that approach lighting system, that credit, it was giving you a much better visibility value, is no longer allowing you to go down to a half. It's out of service. So now you have a new visibility minima of 3/4 statute mile. Okay, this will come up, whether it be here at ADA or in an interview. They're going to try to trick you, and you're going to think you're good with that half statute mile, but because of the NOTAM, it changes what you would normally expect to have. Any questions on that concept? You guys haven't looked at too many NOTAMs, right? Not a whole lot yet. Yeah, I didn't think so. But per the curriculum, I don't think that happens till next week. So just kind of keep that in mind. You'll look at those more and more. So again, things to consider with the ILS. The ILS system has two components, a glide slope and a localizer. Okay, an ILS approach is going to require both the localizer, so the lateral guidance, and the vertical guidance to be operative. You have to have both, okay, in order to fly the full ILS approach. However, an approach can still be flown if the vertical guidance is NOTAMed unusable. So if you don't have that vertical guidance, there's still a portion that can still be flown, and that's just the localizer. That's only providing the lateral guidance. Let me show you what that looks like. So again, at the bottom of an approach plate, you have a section for the ILS, which requires both localizer and glide slope. But there's also a section that says localizer. And this is the section you're going to look at if the glide slope is out of service. So you no longer have that vertical guidance. So your minimums are a lot higher. You can see that, 837 versus 1020. But that's because you don't have that vertical guidance anymore. So they've increased the minimums. So you would be looking at a different section of your approach plate. Now, the last bullet point over here was saying that, and this is good for you guys to know, the lowest landing minimums for a standard ILS approach is going to be a 200-foot ceiling and a half statute mile visibility. That's the best you can get, okay, for a standard ILS. And anything higher than that on a standard ILS just means that there are obstacles out there that you're trying to avoid by having an increased ceiling and visibility above the standard. So, but the biggest takeaways, it uses a glide slope and a localizer for vertical and lateral guidance, and you have a standard ceiling of 200 and a half statute mile visibility. And that standard ILS that we were just talking about is classified as what we call, you'll hear this often, as a Cat 1 approach. Okay, and with that Cat 1 standard ILS, there's really not a whole lot that is needed. Your pilot just has to be instrument rated. They have to know how to use the instruments in their cockpit to fly it. But that's really it with that. Then you have what's called a Cat 2 and a Cat 3. These ILS approach types are going to allow you to go below that standard half statute mile and 200-foot ceiling. So you can see here it drops, the ceiling drops. And then over here in Cat 3, it drops even more. And then here's a different depiction of it. Cat 1, and then Cat 2, you can get even lower, and your visibility is even reduced. See the distance from my runway? And then Cat 3 has 3 different subtypes. Basically, with a Cat 3, this is where you can land in 0-0. So a 0 ceiling and a 0 visibility. But your aircraft has to be equipped properly. Your pilots have to be trained. Your airline has to be given the different operation specifications to do that. So just know that there's a Cat 1, Cat 2, and Cat 3 ILS categories. And the one that you'll be working with to start out is this Cat 1 approach. Okay. Any questions, you guys, with an ILS approach? Okay, that's the one that you will hear about the most often during this class. So we have about 5 more minutes before our next and last break. So let me continue with the discussion, and we're going to transition now from ground-based, using ground-based components, to more satellite-based components. Okay. Satellites are, a wonderful tool that help us more and to be more efficient as we're navigating throughout the airspace. It also provides us with an opportunity to have approaches, and we're not going to get into the specifics here today, but there are instrument approaches out there, a lot of them, that use GPS for navigation. And you're going to see the two types as you continue on in this journey. You'll see RNAV GPS, and then you're going to see RNAV RNP. And this just means area navigation. It's more point-to-point navigation because we're using satellite systems, GPS. We're not limited to the location of these different ground facilities that are physically on the ground, right? And this RNP stands for Required Navigation Performance. If you see an approach with RNAV RNP listed, this is going to require authorization. Your aircraft have to be equipped properly. Your pilot has to be trained properly. And number 3, your airline has to be authorized to fly one of these approaches. Okay, so there's within that satellite-based navigation, you'll hear about these two quite a bit, RNAV GPS and then RNAV RNP. And we're just introducing that to you today. Nothing too serious to remember. Okay, so the Global Navigation Satellite System, okay, is a constellation of satellites that are providing a high frequency signal that contains time and distance that is picked up by a receiver on board the aircraft. So the receivers are going to use a technique called trilateration to determine a point in space. So we'll talk about trilateration here in a second. There are 4 different global navigation satellite systems in existence today. The one that you guys know the most, the one that we're going to be focused on, is the GPS, Global Position Satellite System from the United States. There's also GLONASS from Russia, Galileo from Europe, and Beidou from China. So these are the different global navigation satellite systems out there today. So for the GPS, our system here in the United States, it's going to consist of 31 different satellites around the globe, right? Orbiting the Earth. And these satellites, again, are transmitting a high frequency signal that's being picked up by the aircraft. And in order for the aircraft to use those signals effectively, it has to at least track 4 different satellites. And then for aviation purposes, we actually need 5 or 6 satellites. And the reason for that is so that we have a system, an augmentation system that helps improve the accuracy and integrity of our GPS signals by having these additional satellites. So what are the different uses of a GPS system? Well, we can use them to help us create different freeways in the skies. You may have seen on previous slides the freeways in the skies being either a black line or a blue line. Well, the difference between the blue and black lines for those freeways in the skies have to do with whether they are developed using the VORTAC or the ground-based nav aids. Those are black. And the blue freeways in the skies are those freeways in the skies that are used and determined using GPS. So that is one reason for our GPS. It also helps us create and allows us to create different waypoints, different points in space, simply based on a lat and long coordinate. So we can plot a position anywhere we want it has a Latin long coordinate, and then we add that system or that Latin long coordinate into the GPS database, and the GPS can fly to that known Latin long at any time. And as we've already mentioned, GPS systems can be used to help create instrument approaches, right? We have the RNAV GPS and the RNAV RNP. These are different approaches that can be used to navigate down to an airport simply using the GPS. So with that, you guys, let's go on our 10-minute break. Be back at, let's do 5 minutes or 55 minutes past the hour. And I'll go ahead and put a timer up here at the top for 10 minutes. See you in just a few. You guys can all see that timer, can't you, at the very top? Okay, cool. All right, let's keep going so we don't have too much longer. You guys, we got to the bottom of the hour. So we'll keep chugging along here. So everybody can see the types of navigation slide? Still good? All right. So how does the GPS work? It uses a technique called trilateration, which involves the measuring of distances. So we try to make sure that you guys understand that it's not triangulation that it's using, which involves the measurement of angles, rather trilateration. It involves the measurement of distances. So here's a very simple, very, very simple depiction of how a GPS system works. We're only going to use 3 satellites here just to kind of prove a point. All right. We have 3 satellites here, and we don't quite know where our aircraft is at the moment. We don't know where these signals are being sent to, other than we know that the GPS signal has been sent out this far. So this range here. So we know the aircraft's somewhere around here. If we introduce a second GPS, then we know that, all right, again, this GPS signal was sent out this far, and they intersect here. So now we got a better idea of where our aircraft might be. If we introduce a third satellite, then we can better pinpoint where the aircraft is located based on the distance from all of these different satellites. Now, as you continue to introduce more satellites, your position is going to be greatly, as far as accuracy is going to be increased. You're going to be able to determine speed and all sorts of other things, and even your vertical height above even the ground. So, that goes into it a little more deep than what we need to know, but this is the gist of how the GPS signals are being used with the GPS receivers on board an aircraft. Now, your GPS signal is only as good as its accuracy, right? I typically use the example of me jumping in my car. I pull out my phone and I say, hey, I want to go to Home Depot. And instead of taking me to Home Depot, it takes me to McDonald's. And everybody knows I do not need to go back to McDonald's. I probably go there too often. So, I want an accurate GPS signal. And, at the same time, I don't want to be driving down an interstate and the whole time my GPS thinks that I'm off in somebody's, cornfield. So same thing, but much more serious when we're talking about an aircraft, right? Where you're using the GPS signals to navigate in the skies, where you have a lot of other aircraft traveling in opposite directions. You want that GPS signal to be as reliable as possible. And in order for that to be the case, we have different GPS augmentation systems, right? Different ways of ensuring the accuracy, the integrity, the availability of these GPS positioning systems. One of the systems is called the RAIN system, or the Receiver Autonomous Integrity Monitoring, RAIN. And this is important for you guys to remember up to a certain extent, right? That we have 2 augmentation systems, that being RAIN, Receiver Autonomous Integrity Monitoring, and the second one being the Wide Area Augmentation System. And we use the acronym WAAS, WAAS, to refer to that one. Okay, the 2 different augmentation systems. Let's talk first about RAIN. RAIN is going to help, again, monitor the integrity of a GPS signal that is being transmitted from a satellite and then determine its reliability. In order for us to use RAIN, RAIN is going to require the use of 6 satellites. And what this does, it allows the RAIN system on board the aircraft to isolate a corrupt satellite signal and it removes it from the aircraft's navigation source. Okay, so it's not using a corrupt signal. Now, if the aircraft has on board what we call a baro-aided GPS system, which basically allows the onboard computers of the aircraft to use the static system information, meaning that it's able to take the different outside air temperature and pressure and calculate a height above the ground. Okay, it has that capability. In that instance where the aircraft's GPS system is able to determine the height above the ground, because of this baro-aided system, it can do all of this with just 5 satellites rather than 6 satellites. That 6th satellite was actually helping with determining the aircraft's altitude. But you can do away with 1 less satellite if your aircraft is equipped with what we call a baro-aided GPS system, where it's able to calculate the aircraft's height. Okay, but again, it's pretty cool. The RAIN system uses those satellites. It's able to monitor the satellite signal and then kick out a bad satellite and replace it with a good satellite if it detects some sort of error in the satellites being used. The RAIN messages. Oh, yeah. Sorry, guys.
I had a question. I'm sorry.
Yeah.
I just wanted to ask, what creates a corrupt satellite signal? How does that get?
Good question. Yeah. Sometimes, and that's over here. The causes of a RAIN outage or just a bad satellite could be just number one, there probably are not enough satellites out there to give you a good GPS reading. Maybe there's poor satellite geometry. Okay, just the way that the satellites are positioned is just not positioned in a good spot to provide a reliable signal. And it could also be a change in the aircraft dynamics. So the way that the aircraft is being flown could cause some sort of GPS or a satellite error. So in this RAIN message, hopefully that helps. Was that Lakeisha? To kind of give you an idea?
Yes, that helped a lot. Thank you.
Yeah, you bet. And Chris, did you have a comment?
Yeah, if you fly in some of the less friendly places in the world, you can also have some that could be spoofed as well. So it would pick up on that.
Yep, absolutely. Yeah, there could be GPS jamming where they cut off the GPS signal entirely. So, yeah, absolutely. The RAIN messages. So the receiver autonomous integrity monitoring, while it's monitoring all of that, if it detects something, it will spit out some sort of message. Hey, there's not enough satellites available to provide RAIN, or RAIN detected a potential error. So in that instance, you would most likely revert back to what we call ground-based navigation, or green needles. You'll hear that from time to time. And that just means that you're no longer relying on the GPS for navigation. You're tuning in to those radio frequencies now. You're tuning into those VORs to help navigate from point to point. So that's just one augmentation system, right? An augmentation system, again, means that it's a system that helps ensure the availability, integrity, and reliability of a GPS signal. Okay, and RAIN is one of those ways of doing that. And RAIN would be considered the older big brother, okay, of what we call WAAS. WAAS is the second one. WAAS is like the new baby brother. It's new, it's shiny, it's wonderful. It is a really incredible augmentation system that is out there today. Okay, so WAAS, Wide Area Augmentation System, is your second GPS augmentation system that you need to know about. And it too has been designed to improve the accuracy the integrity and availability of a GPS signal. Here's how it works, and I'm going to kind of just summarize this the best I can. But there are these different wide area reference stations out there throughout the United States. And each of these different wide area augmentation systems have been surveyed. And we know precisely the lat and long coordinate of this wide area reference station on the ground. Then you have these different GPS satellites out there. And that GPS satellite is trying to determine the location of all of these wide area reference stations. And if for whatever reason, the wide area reference station determines that the GPS is not determining the correct lat and long of this wide area reference station, it will help recalibrate that GPS signal so that it determines its correct position, and then it will send that calibrated information out to a wide area master station, then to a ground earth station. It will uplink it to another communication satellite, and then if the aircraft is equipped with a WAAS receiver, the aircraft can then receive corrected GPS information. And it's doing all of this in a matter of just seconds. So very fast. And so what it's doing, again, it's saying, well, if these satellites are determining an incorrect position down here, then it's most likely giving an inaccurate location for where this aircraft is at. And so what it's doing is it has the ability to detect the incorrect lat and long and the bad calibration. It's able to send all that corrected information back up to a satellite and then give corrected information to the aircraft so that the aircraft's position is corrected and accurate. And it's all happening very, very fast and constantly. So, and because of how quickly these corrections are taking place, the wide area augmentation system is so precise that it has gotten to a point where the GPS approaches, if it can use WAAS, then we can provide approaches into airports that are remote into Alaska that have the same accuracy as those found with an instrument landing system or components that are used on the ground. So because of WAAS, again, we're able to provide not only lateral, but more precise vertical navigation using GPS, which allows us, again, to get into airports that are much more remote, that don't have the funding nor the ability to install these ground-based components to, okay, because they cost a lot of money. And so they're hard to install, especially if you're in an area like Alaska with a lot of terrain. Okay, there's just not that flexibility for that. So yeah, the WAAS augmentation system has really reshaped and has changed the aviation industry in the way that our pilots fly into and even out of airports because of how precise we can get our procedures now using GPS. Do I have any pilots out there that have had the opportunity to fly an aircraft that is equipped with WAAS and have flown, say, like, for those of you who understand what I'm talking about, an LPV approach? Is there anybody out there that's done that? Brett, done it?
Yeah, I do it all the time with students.
That's awesome. What are you flying? Like a G1000?
A Garmin G3X or a GTN 650.
That's awesome. Cool. So yeah, you know exactly what we're talking about here. And I mean, you can probably see the benefits of it, right?
It's very nice. It's very
it is.
convenient because there's only one ILS approach in Phoenix, but every airport has an LPV.
Absolutely. Pretty cool. And I'll just throw this out there. The way that an ILS approach looks at obstacles for obstacle avoidance is the same way we look at obstacles for an LPV approach. And I know some of you may not understand that, but I'm just trying to tell you that it's exact. It is so precise that we're able to mimic the ILS procedure now. And it's all because of how we're augmenting and how we're ensuring the reliability of these GPS signals using this system in front of you right now, the WAAS system. So pretty cool. Excellent. Well, again, just remember, we want reliable GPS signals. And the way we do that is by having two augmentation systems. What was the first one we learned about?
RAIM.
RAIM. Perfect. And that's receiver autonomous integrity monitoring. So it's using a number of different satellites, right? It's looking at it and going, hey, satellite number 3, you're not performing very well. Get out of here. And it replaces it with a new satellite. Okay. That's how that one works. Then you have your number 2, which is the WAAS. And it's this system here where it's able to detect errors, correct it, and send corrected signals back to the aircraft very, very quickly. So it's constantly getting accurate and updated GPS information. Okay. All right, you guys. Well, we have about 15 more minutes, and I'd like to end on this topic right here of instrument departures and arrivals. We refer to this as our SIDs and STARS. Okay. SID stands for Standard Instrument Departure. STAR stands for Standard Terminal Arrival Route. So you can think of it as departures and arrivals. And again, this basic information that I'm giving you right now, especially on this page, is important to know. You need to know what a SID is, what it stands for, and the STAR. Okay? And the purpose of a SID and a STAR, a departure and an arrival, is to help sequence air traffic in and out of an airport environment with a reduced workload for the air traffic controllers and our pilots. And both of these procedures, the SID and the STAR, are designed in such a way that it will help ensure obstacle clearance. Okay, whenever it's flown. So here's it. I'm going to advance the slide, and there's going to be a lot of stuff on there that you don't know, but you don't need to know it yet. Okay, so don't worry. This is a SID. This is a departure that the pilots refer to, and our air traffic controllers know about these procedures. And the pilot is going to follow this to a T. They're not going to deviate from it at all, because it has certain courses to fly to these different points. It tells them what altitudes they need to be at, and even sometimes a certain speed to maintain. And what happens is, because the pilots have been told to follow this specific departure from ATC, or air traffic control now knows exactly what their pilots are going to be doing. So that reduces their workload. That reduces the need for the air traffic controller to constantly tell every pilot and every aircraft what they need to be doing as they're leaving an airport. Okay. And let me zoom in here. I just want to show you, this is the airport that they're departing from. And you can just see, if you kind of just get the big picture idea, right? You can see that the aircraft are departing and they're all getting to a point where they're getting funneled out to these different areas. Okay, that's what a departure does. They leave an airport and then they start going into the direction of their final destination. Okay, so a SID is simply a standard instrument departure that reduces the workload for air traffic control and for the pilots. And you can see that it's helping funnel aircraft out and help it disperse aircraft out to different areas away from the airport that they've departed from. That's all I want you to know for today. Okay. Any questions with the departure? A SID. Okay, here's an arrival. So now my airport's over here. Okay, this is a STAR, a standard terminal arrival. Now we're taking aircraft from the en route environment, from those freeways in the skies, right? We're getting them to a point where they are funneling now into the airport. You're bringing aircraft in now. As a dispatcher, you're going to know, let's just stick with my scenario, Denver to San Francisco. You're going to need to pick a departure, a SID, that goes out more towards the west than, say, out towards the east, right? That would make sense. I'm going from Denver to San Francisco. I need to be going west. So you're going to be looking for a departure that goes out that direction. And then for San Francisco, you need to be looking for an arrival that's coming from the east. Okay? And you piece those two things together. It's kind of like making a sandwich. That's what I've always said. You got to figure out your departure, figure out your arrival, and then you'll fill everything else in between, because now you know where to connect the two pieces. Okay? So again, a SID, everything's funneling everything out of an airport. A STAR, an arrival, you're bringing aircraft into an airport environment. And before we end, I do have this example. It's a flight from Oklahoma City to Salt Lake City. I always say I'm feeling a little homesick, so I got to go back home. However, I couldn't go skiing in Salt Lake right now, I don't think. It wouldn't be all that fun. I think we got more snow in Oklahoma City this past week than Salt Lake has the entire winter. So, but again, as a dispatcher, you are going to create a flight plan that shows your routing, the route that you're going to take to go from, say, Oklahoma City to Salt Lake City. And within that flight plan that you create and send to air traffic control, there's all these different codes. And part of that code is going to show them your departure, and it will also show them at the end your arrival. How are you leaving Oklahoma City? And how are you arriving into Salt Lake City? Okay, this is a route from OKC to Salt Lake City. This is a real route that's out there. And let's break this down just a bit. So at the top, I have that flight plan, okay, the routing. And at the beginning of this routing for Oklahoma City to Salt Lake, it says Stephen 3. Okay, Stephen 3 is my departure out of Oklahoma City. Everybody good there? We're leaving Oklahoma City on this departure that has a name. It's called the Stephen 3 departure. Okay. And there are a lot of different ways I can leave Oklahoma City. I can depart from the north, I can depart from the south. But long story short, I'm trying to make it out here to this fix that's going out to the west. Okay, it's called ZWE. And if you look at my routing, that's what I have. I've told ATC that I want to leave Oklahoma City using the Stephen 3 departure because it goes out to the west. And I also specify the last point on that departure, which is ZWE. And I've told them that. And the pilots are going to use these different departure route instructions down here, depending on how they take off. But you don't need to know that, right? You just know that, okay, I want to depart Oklahoma City and I want to go out to the west. This SID does that. So I'll depart and go out to ZWE. And that's what I've added in my routing. Okay, Stephen 3 ZWE. And you guys, as we keep getting deeper into this week and more next week, towards the end of next week, you're going to see this more and more. You guys are going to have opportunities to put together these routes. So just remember that in my routing, the first thing listed is my departure. The last thing listed, right, is my arrival. So the departure name, and then the last point of the departure is ZWE. And then here is everything en route. This is where you're kicking back in the aircraft, right? Coke, peanuts, all your treats. That's this section of your flight. And then when you get to this point, helper, okay, helper is one of the first spots where you can begin your arrival into Salt Lake City. So you got to fly from here all the way in. Okay, so for the arrival side, you specify the first point of wherever you want to start your arrival. That's the first one. And then the last thing you list is, well, what arrival is it? It's the Spain 8 arrival. Okay. So for the departure, you always list the departure name first and where you want to go on that departure. And for the arrival, it's opposite. For the arrival, you got to specify what point are you starting your arrival on, and then list what arrival you're using. So helper, right here, helper. And then we're using the Spain 8 arrival into Salt Lake. Okay. So again, think of it like you're making a sandwich. If I'm building a flight from Oklahoma City to Salt Lake, I first need to know my departure. I'm going out to ZWE. And then I skip over to my arrivals and I'm like, okay, this makes sense. Helper, that would be good for a flight coming from the southeast, right? I can start right there at helper and I'll use this arrival. And then you can fill everything else in between. You can make the connection better. Okay, that's kind of the technique that you need to have as a dispatcher when you're building your route. Let's figure out my departure out of the airport. Let me figure out my arrival, and it ends here. So my arrival starts here, and my departure ends right here. So now I just have to figure out how to connect these two together. And then you have your route. Okay. And again, like I said, next week, you guys are going to actually be introduced to SkyVector with the purpose of actually planning and coming up with a route. Okay. That's all you're going to do with an instructor. You're just going to go in there one right after another. And all right, let's build a route from here to here, here to here. So all day long, you're going to be picking departures and arrivals and then filling out the en route portion of your flight. Okay. What questions do you guys have for me with regards to a SID, a STAR, and your flight plan, your routing? Hopefully that you guys get the big picture, right? I'm not expecting you guys to know every single detail, but are you guys grasping the big picture concept?
Is there a particular amount of points you have to have in it, or is it just dependent on how long the flight is?
Nope. Yeah, it really just depends on how long the flight is, right? And how you end up planning that route. I could have a room of 30 dispatchers, and we could have probably almost 30 different types of routes that are legal. So it really just depends on how you end up building that route personally. So, and I would say there are more effective ways than others, right? But it doesn't necessarily mean that it's wrong. So yeah, and they're going to show you all of that come next week on, I think it's Friday of next week. Yeah. Again, I have to take very complex concepts and introduce it to you at some point before the application side of things. And that can be difficult for you. I understand, but I don't want anybody to be discouraged, right? You're not there yet. You're not at the discouraged point. So just, we talked about this today. You've been introduced, and expect more information to come later on. So we'll build upon these concepts together. But yeah, any other questions? I thought I saw another hand, but maybe not. Okay. Well, again, before we drop off, again, I will have 2 YouTube links for you guys to watch before tomorrow's class. Please watch the videos if you can. I think it's going to help greatly with the material that we're going to cover tomorrow. We're going to talk about the low and high IFR en route chart. That's what you see behind here, this whole mess. We're going to talk about this. We're going to actually make sense of this tomorrow. Okay. But please watch the video that I have on the, there's a little section in there specific to the altitudes that you'll find on this chart. And I think it's a really great video to introduce what those different altitudes are for when we get into it as a class. Okay. And then the second video will be about the instrument approach plate. What is the instrument approach plate? And it kind of breaks it down from top to bottom. It'll be the same thing we do tomorrow in class, but the more that you hear it, the more it'll stick. So I really do like to have my students watch those 2 videos before we dive into those concepts in class number 2 with me. So please watch those. And I will also include the slides that we covered today for your review. And as always, I will be here for another 15 minutes or longer, depending on how long you need me and depending on how long you want to stay. But that's going to be the end of our class today. Thank you guys for sticking around. That was a lot of information, but we'll pick back up tomorrow. Okay. We'll see you then. You guys have a good night. Thanks, Betty.
You're welcome.
See ya. Hey, Brian,
Yes.
You got a question?
Hey, yeah, I'm probably way jumping ahead here, but I'm just curious.
It's easy to do.
Yeah. So I feel like with all of this, I mean, we plan our routes and all this stuff, but I feel like there's still a big elephant in the room, and that's the ATC. Because don't we have to submit the flight plans to ATC for approval? And I'm asking, will we go into that component of the whole thing during this class, during this course?
That's a really good question. No, actually you don't. That happens in the background for an airline. So what happens is really what's going to happen is you're going to have what we call canned company routes. And your company has like an ATC department, and they've said, okay, for this one flight from Oklahoma City to Salt Lake, here are the 10 routes that we want as our company routes. And they've already been vetted from ATC and they've been scrutinized, right? And 9 times out of 10, you're going to pick from one of those company routes when you're in the dispatch seat at work. You're not going to be creating routes every single flight. You don't have time for that. You're going to be company route 001. Perfect. It looks good. I'm using it. That's the default route. The weather's good. Not even going to think about it. Every now and then there's a big nasty thunderstorm, or ATC, which we'll talk about next week, will tell you that they want you to come into an airport a very specific way. In that instance, you'll have to modify the route if it's not already built in the system at work. Not a big deal. They'll show you how to modify a route. But again, 9 times out of 10, it's already been entered into the computer system at work, and you get to choose and just go click happy through 10, 15 different routes and go, no, yes, no. Like, you just get to pick. And it's really easy. Nothing cosmic. Again, here in class, they're going to tell you again, build me a route from Denver to San Francisco. And they'll throw in an issue with the aircraft. You can't be like, so there's an MEL, remember the minimum equipment list item? Like,
Right.
Something's out and now I want to fly at 34,000 feet, but now you can only fly at 26,000 feet.
Yeah.
Right.
Okay.
So, but no, and if you do modify a route at work, whatever route you come up with gets sent to ATC digitally. You hit the button and it files that flight plan with ATC. I mean, if you did something really wrong and completely wacky, when your pilots go and pick up their clearance, they're going to say contact company. They're going to be like, whoever put this flight plan in here is dreaming. They're never going to get that.
Yeah.
So contact company. And you may, I think I've gotten a couple myself where it's like pilot calls in and goes, hey, ATC does not like this flight plan. And I missed a section or something, it happens. But yeah, it's, you don't do it as often as you think you would.
Okay. Is there any, so like, let's say your airline has, some preset routes for between two places.
Company routes. Yep.
Yeah. And is there anything you can do, or is there any part of the job where you can look and see kind of what ATC is doing that day with airplane and maybe try to pick one of the routes that might match more like how they're sending planes? Like the route they're sending planes on?
Mm-hmm.
Okay.
Yeah, there are a few. So sometimes you have FAA, ATC initiatives that are happening where they tell you specifically where they want you to go to get into or out of an airport, and those are publicly known, and you'll have access to that.
Okay.
And the company will tell you how to access that. Other times it's me just looking around. Let me zoom into an airport and see where they're coming from.
Right.
And then I can piece together things from that, right? So yeah, there are a lot of resources that you'll learn about, sometimes very company specific,
Mm-hmm.
and you kind of just go off of that. But yeah, there are like FAA traffic initiatives that are just going to be known. You're going to be like, oh yeah, they want me to do something specific.
Okay. But yeah, but it sounds like what you're saying though is more of that kind of training is going to be more company specific. Okay.
Yep. Yeah, we teach you the nitty gritty stuff, right? The things
Right.
you'll probably never do again, but then you're going to be like, oh wow, Dallin's right. This is easy. That was harder. This is easy. So,
Yeah.
and like I said, wait till next week. You have a whole day the whole day is just being in SkyVector and building random routes with an instructor. It's really easy. You'll understand it when they start talking about it.
Cool.
Yeah.
All right. Thanks, man. Appreciate it.
You bet. You bet. Yeah, no problem. Anybody else? With questions?
Yeah, it's the
Trevor?
same question as Betty. What did you say that you're going to post the video links in the classroom, or?
Yes, on the Google Classroom, the forum where Jaden typically posts. I think he put like a METAR quiz and Legal to Go quiz on there yesterday.
Okay, cool.
Yeah. Do you know where to go, guys? Do you know where that is? Am I saying it right? I think it's the Google Classroom announcements page.
Yeah, it's like the feed or whatever. Cool.
Yeah, and I'll add those on tonight right after this call. I'll just write a little message and then throw those in there for you.
Awesome. Thanks. Have a good night.
And they're short videos too. They're not very long, so it won't take very long to look at. Yep.
Thanks. Have a good night.
Hey, thanks, Brian. See ya.
Thank you.
You bet. No problem.
Bye. Bye.
Hey, bye, Betty. Take care. Hey, Mohammed, do you have any questions? Oh, is it Siwar? No. Okay.